95% of the universe is made of something we do not understand. So what does that say about the 5% we call reality? Our galaxy feels less like a triumph of creation and more like an unresolved accident, suspended in a silence we barely understand. Born from what appears to be nothing, it is only one among hundreds of millions we may never see. Adrift in an immense universe, each galaxy carries its own hidden history, yet all circle the same disturbing question: how does something emerge where there should be nothing at all? The universe reveals itself as an ever-expanding assembly of galaxies, stars, planets, matter, and energy, vast enough to unsettle any sense of certainty. Modern cosmology places its beginning around 13.8 billion years ago, in the Big Bang, a violent origin that marks the start of everything familiar. From that moment, space itself began to stretch, shaping the cosmic web we now observe. We have learned that everything we know, stars, planets, even ourselves, accounts for only about 5% of the universe. The remaining 95% is dark matter and dark energy, unseen forces that sculpt cosmic structure and drive expansion, yet remain stubbornly beyond direct detection. As understanding deepens, the scale becomes harder to grasp. The universe spans billions of light years and contains an estimated 2 trillion galaxies, each filled with billions of stars and countless planets. This immensity quietly erodes any sense of centrality or importance. The laws of physics appear consistent everywhere, governing galactic motion, stellar life cycles, and the subtle behavior of particles. These laws allow astonishing predictions, from planetary orbits to the behavior of black holes, objects so extreme that even light cannot escape. Yet even here, certainty falters, especially when confronting dark energy, the force seemingly accelerating the universe's expansion. Observed through distant supernovae, dark energy works against gravity, pushing galaxies apart faster and faster. Its existence reshapes our expectations of the future, hinting at a cosmos that grows colder, thinner, and increasingly isolated. The Big Bang theory remains the central framework for understanding this story, tracing the universe back to an intensely hot and dense beginning, followed by relentless expansion. Evidence accumulates in its favor, including the cosmic microwave background, a faint, uniform afterglow that captures the universe, as it was just 380,000 years after the beginning. This radiation, uniform across the sky, reinforces the idea of a hot, dense origin and leaves little room for comfort. The redshift of galaxies adds to this unease, showing that space itself is expanding, that everything is moving away. The farther a galaxy lies, the faster it recedes, implying a universe once far smaller, hotter, and more compressed than imagination easily tolerates. The theory also accounts for the observed proportions of light elements formed in the universe's earliest minutes as matter cooled enough to assemble into nuclei. Yet, acceptance does not bring closure. The Big Bang leaves unanswered what came before, or what exists beyond what we can observe. To address internal contradictions, it introduces cosmic inflation, a brief but extreme expansion that smoothed and flattened the universe at its earliest moments. Observations align with this picture, but alignment is not reassurance. After the Big Bang, the universe began its long expansion from an almost inconceivably small state into the vast, fragile cosmos we inhabit now, a transformation that feels less like resolution and more like an open wound in our understanding. The expansion is often compared to an inflating balloon, galaxies drifting apart not because they move on their own, but because the space between them keeps stretching. At the beginning, the universe was an overheated, dense mixture of particles and radiation, too violent and unstable for atoms to exist. As expansion progressed, this primal fire cooled just enough for quarks to lock together into protons and neutrons, which then assembled the first simple nuclei, mostly hydrogen and helium, through nucleosynthesis. This all unfolded during a phase of extreme expansion, less than a trillionth of a second after the Big Bang, believed to be driven by cosmic inflation. Inflation proposes that space itself expanded faster than light for a fleeting instant. That idea alone strains intuition, smoothing energy and matter across the universe. and leaving behind the eerie uniformity we now see in the cosmic microwave background. It quietly suggests that on cosmic scales, the rules we trust may bend or even fail. As cooling continued, gravity began to gather matter, shaping the first stars and galaxies. These objects became furnaces of creation, forging heavier elements and scattering them back into space at their deaths, quietly preparing the ingredients for planets and life. Expansion was never perfectly even. Matter and energy pulled it into a vast cosmic web, dense clusters separated by immense emptiness. Galaxies still recede in every direction, and the realization that this expansion is accelerating unsettled cosmology. It implied dark energy, an unseen presence embedded in space itself, pushing outward against gravity. What this force truly is remains unresolved, casting uncertainty over the universe's long-term fate. In the first second after the Big Bang, change came relentlessly. The universe began as an unimaginably hot, dense state, and almost immediately inflation stretched it beyond any human scale of comprehension. In less than an instant, it grew from smaller than an atom to larger than a galaxy. As temperatures dropped, the fundamental forces began to separate. Gravity broke away first, followed by the strong nuclear force splitting from the electroweak force. What had once been unified fractured into the distinct interactions that now govern reality. Within that same second, cooling allowed quarks, once free in the chaos, to bind together into protons and neutrons. This process, Baryogenesis, quietly determined that matter would exist at all. The universe remained a dense plasma of quarks, electrons, and neutrinos, but its internal relationships were already shifting. Protons and neutrons formed, preparing for the first atomic nuclei. By the end of that first second, the universe was still brutally hot and dense, yet the basic forces had taken recognizable forms, and the foundations of matter were set. Everything that followed, atoms, stars, galaxies, complexity itself, depended on this fragile sequence. Quarks sit at the core of all matter, defining everything familiar, yet they remain hidden behind the unsettling logic of quantum physics, a reminder that even the substance of reality resists complete understanding. To think about quarks is to stare at matter and realize it has no solid floor. They are described as the deepest building blocks, smaller than atoms, smaller than protons and neutrons, threaded into the universe's composition, yet never allowed to stand alone. In nature, they do not appear as solitary things. They are always trapped in company, bound into groups that become protons and neutrons, and those, in turn, become the nucleus of an atom. Their origin points back to the universe's first instant after the Big Bang, to the quark epoch, within the first microsecond, when heat and density were so overwhelming that familiar particles could not yet hold their shape. Temperatures climbed into the trillions of degrees. Matter did not behave like matter at all. It existed as quark-gluon plasma, a seething state where quarks and gluons moved freely, not in objects, but in something closer to a raw, indifferent soup of energy. Gluons served as the exchange particles, the glue of the strong interaction, yet even that glue could not assemble anything stable until the universe cooled. Expansion meant cooling, and cooling meant a threshold. Only when the thermal fury dropped far enough could the strong nuclear force take effect. It is one of the four fundamental forces, brutally powerful and yet confined to microscopic distances. A force that does not reach far but does not need to. When it finally dominated over the kinetic agitation that kept quarks apart, quarks began to lock into combinations of 2 or 3, forming composite particles, mesons, made of 1 quark and 1 antiquark, and baryons, made of 3 quarks. Among baryons, protons and neutrons stand out as the most stable and most familiar, the quiet backbone of atomic nuclei. The path from quarks to these recognizable particles is a process that unfolded in the universe's infancy. As expansion continued and temperature fell, conditions became ripe for binding, and protons and neutrons emerged as a crucial step in the chain that would eventually lead to atoms, stars, planets, and life. But at this stage, it still feels precarious, as if the universe is only just learning how to hold itself together. During the quark epoch, everything was a hot, dense mixture of quarks and gluons. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Yet for the protons and neutrons that would anchor ordinary matter, it is only up and down that matter directly. Gluons carry the strong force, pressing quarks into unity even as their charges drive them to resist. It is a strange tension. The same reality that insists on separation also contains the rule that forces togetherness. As the universe cooled from its initial blaze, it crossed the threshold that allowed quarks to combine, again around 1 microsecond after the Big Bang. The strong force began to outweigh the thermal energy that had kept everything unbound, and quarks started forming stable groups called hadrons. Protons and neutrons are hadrons. A proton is 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. That small rearrangement decides everything about their charge. Protons come out positive, neutrons come out neutral. This difference governs how atoms and molecules form and interact, and it makes the early universe feel less like a smooth story and more like a narrow passage, where a slight change in combination would have meant a different kind of matter, or none that we would recognize. The formation of protons and neutrons was a turning point. It signaled the beginning of the end for the quark-gluon plasma and the start of a universe filled with matter as we know it. Once protons and neutrons existed, they could begin gathering into the nuclei of the simplest elements through nucleosynthesis, laying the groundwork for the chemical complexity that would later allow stars, galaxies, and life to emerge. Yet even here, the certainty is unsettling. What we call solid begins as a brief victory over chaos. And as we keep pulling at these first moments, the fundamental forces stop feeling like background rules and start feeling like the true narrative. Gravity, electromagnetism, the strong nuclear force, and the weak nuclear force acted as the architects, shaping whatever the Big Bang left behind into the structures we see now. In the earliest moments, these forces were unified as one. Then expansion and cooling drove symmetry breaking, a splitting of what had once been a single behavior into distinct laws. Gravity separated first, shaping the large-scale structure of the universe by steering the motion of galaxies and clusters of galaxies. It is the weakest of the 4, and yet its reach makes it inevitable. Its influence grows with mass and distance, until it dominates the cosmos simply by refusing to let go. After gravity, the strong nuclear force separated, the force that holds atomic nuclei together, overcoming the electromagnetic repulsion between positively charged protons, as if the universe must constantly fight its own urge to fly apart. It was in that splitting moment that quarks finally locked together into protons and neutrons, not as a choice, but as a consequence. The strong force held fast, letting stable nuclei exist at all, and quietly preparing the way for the first atoms. As the universe kept cooling, the weak nuclear force and electromagnetism separated next, as if reality itself was sorting its rules in the dark. The weak force sits at the heart of nuclear fusion and radioactive decay. It steers the lives of stars and the slow making of elements heavier than hydrogen. Electromagnetism governs every charged encounter. It drives light, electricity, and magnetism. It shapes atoms and molecules, and with them, the chemistry that life depends on, whether we like the implication or not. Together, these forces push the universe from a near-uniform particle haze into something structured and uneven: galaxies, stars, planets, then life. They also set the conditions for the first hydrogen and helium atoms to appear in recombination. That shift made the universe transparent to light. It also released the cosmic microwave background radiation, a leftover glow from that time, a frozen glimpse of infancy that still feels too direct to be comforting. The same interplay of forces helped guide the rise of stars and galaxies. Gravity drew matter inward. Electromagnetism and the nuclear forces controlled what happened inside stars, including nuclear fusion. Fusion kept stars burning and produced the heavier elements that later became essential for planets and for life. Formation of atoms and molecules. We turn to the first atoms, because this is where the story stops feeling smooth. This event, recombination, happened about 378,000 years after the Big Bang. Before it, the universe was a hot, dense plasma of electrons, protons, and photons. The energy was so relentless that any attempt at an atom would be torn apart almost immediately. Expansion kept going, cooling followed. Then, at last, the first atoms could survive. Hydrogen formed first, the simplest and most common element, one proton, one electron. And suddenly, the universe had something that could persist. Helium came soon after, slightly more complex, with 2 protons, 2 neutrons, and 2 electrons. These early atoms became the base layer for the chemical diversity we see now. A turning point, not because it was dramatic, but because it changed what the universe was allowed to become. Once atoms were stable, they began to gather under gravity. Slowly, almost unwillingly, the first stars and galaxies started to take shape. This era opened the door to chemical processes that would eventually lead to planets and to life itself. After the first atoms, another shift arrived. The first molecules. The move from lone atoms to early molecules marks a crucial chapter, laying groundwork for the chemistry that defines the universe we recognize. The way these first molecules emerged is a reminder that the cosmos does not explain itself. It simply proceeds, and we chase after it. As expansion continued and temperatures fell, conditions became friendlier to newly formed atoms, mostly hydrogen and helium. Hydrogen, with its single electron, was especially ready to bond with other hydrogen atoms. Molecular hydrogen, H2, appeared. A small step in structure, but a serious change in what could happen next. This simple molecule mattered. It became a first tool of early chemistry. It helped gas cool. Cooling let gas clouds collapse more efficiently under gravity, which pushed the formation of the first stars. Those early stars became the furnaces, where the first heavy elements were made. Elements that would later shape planets, asteroids, comets, and living organisms. The exact timing of the first molecules is still under active research. It is thought to have happened a few 100,000 years after the Big Bang, not long after atoms formed. This period set the stage for the continuing interplay of forces that built the universe's structure, from galaxies to planets, and toward the raw conditions that made life possible. When we trace that lineage back, hydrogen and helium stand there at the start, foundational and a little unsettling in how much they decide for everything that followed. These two elements, the simplest and most common in the cosmos, weren't just present, they quietly dictated the universe's earliest shape. Their weight in that first era is hard to grasp, because they were the primordial universe. Everything that followed, every structure and every thread of chemistry we now call the cosmos, was forced to begin here. After the Big Bang, there was mostly hydrogen and helium. Hydrogen, the lightest element, one proton and one electron, dominated the early matter. Helium, heavier with 2 protons and 2 electrons, came next. And somehow, this spare inventory was enough to set everything in motion. Their simplicity mattered. It made them the raw starting point for all later elements and molecules, forged through nuclear processes inside stars. Hydrogen's role went further than sheer abundance. It sat at the center of the first stars, the population 3 stars. Those first stars were massive, hot, brief. They didn't last long enough to feel stable, but they were essential. In their cores, fusion pushed matter into heavier forms, and when they died in violent supernovae, they scattered those heavier elements outward, contaminating the clean early cosmos. That spread made room for new stars, for planets, and eventually for life as we recognize it. Helium's role was less tied to chemical variety, yet it still shaped what stars could become. Its presence steered stellar evolution. Stars fuse hydrogen into helium in their cores, releasing immense energy and light. With age, stars begin fusing helium into heavier elements, shifting their fate and branching into different outcomes. That slow internal change helps explain why the sky contains such a wide range of objects, not one uniform kind of star repeated forever. Even the hydrogen to helium ratio carries an uneasy clarity. It points back to the early universe's conditions and aligns with the Big Bang theory. Observations of primordial helium, alongside the cosmic microwave background radiation, keep insisting on the same origin story. A beginning that was hot, dense, and nothing like the calm we imagine when we look up. Cosmic microwave background radiation. Moving deeper into the cosmos, after tracing hydrogen and helium, we reach another pillar of cosmology, the cosmic microwave background, the CMB. It is the Big Bang's afterglow. Ancient light still filling the universe, still touching everything, like a snapshot the cosmos never managed to throw away. It was discovered by accident in 1965 by Arno Penzias and Robert Wilson. Since then, it has stood as a central piece of evidence for the Big Bang, a way to look back to when the universe was about 380,000 years old. By then, the universe had cooled enough for electrons and protons to combine into neutral hydrogen, a transition called recombination. Before that, the universe was a plasma, charged particles and photons packed together, constantly scattering. Light could not travel far. It couldn't carry a clean message. But as expansion continued and temperatures fell, photons began moving freely. The universe turned transparent. The CMB is what remains from that moment, stretched into microwave wavelengths by billions of years of expansion. Its importance is not only that it supports the Big Bang theory, it is that it holds detailed information about the early universe's conditions, encoded in tiny temperature fluctuations. Those minute differences in temperature and density are believed to be the seeds of everything that exists in large-scale form today, galaxies and clusters of galaxies. Measurements of the CMB have allowed precise estimates of fundamental parameters: the universe's age, its composition, and the rate of its expansion. For example, CMB data point to an age of about 13.8 billion years, with roughly 5% ordinary matter, 25% dark matter, and 70% dark energy. The numbers feel clean, but the implications don't. Pushing further into this narrative, the CMB sits beneath the Big Bang theory like a pressure point. The theory says the universe began in an extremely hot, dense state and has been expanding ever since. The CMB is one of the most direct observational remnants of that beginning, a tangible trace rather than an idea. Its near uniformity, a temperature around 2.7 Kelvin, almost the same across the sky, is unsettling in its steadiness. Yet it is not perfectly smooth. It is marked by tiny fluctuations. Those small variations matter because they imply regions of slightly different densities. They are the early imbalances that grew into all the structure we now see, from galaxies to clusters of galaxies. The Big Bang theory predicts that after the initial event, the universe was searing, dense, and filled with particles and radiation. Expansion brought cooling. Cooling allowed neutral atoms to form. Neutral atoms allowed photons to escape. The CMB is the relic of that release, stretched into microwaves by the expanding universe, still visible today as the lingering afterglow of that first, overwhelming moment. Furthermore, careful readings of the CMB's tiny temperature ripples through missions like COBE, Cosmic Background Explorer, WMAP, Wilkinson Microwave Anisotropy Probe, and Planck have yielded strikingly precise numbers for the universe's age, its composition, and how fast it expands. Those numbers line up almost unnervingly well with what the Big Bang theory predicts. The faint anisotropies in the CMB trace how matter and energy were spread in the early universe, mostly uniform, yet not perfectly so, just small departures. And from those small departures, galaxies and larger structures could emerge. The CMB exists. It carries the expected imprint. Its properties sit in strong agreement with the Big Bang's predictions, as if the universe is still whispering that it began hot and dense, and that it has been stretching outward ever since. Looking into the cosmic microwave background, CMB, has opened new vistas on the universe, but not in a comforting way. This relic radiation, a dim afterglow from the Big Bang, feels like a message that barely survived. It holds details about the universe's infancy and what followed. By studying it, scientists have pulled out insights that reshape cosmology, even as the picture refuses to feel fully solid. One of the most profound results is a confirmed age. From the CMB's minute fluctuations, scientists estimate the universe is about 13.8 billion years old, a single number that tries to pin down everything, from a searing beginning to the present moment. It offers a timeline grounded in measurement, and yet it can feel strange how much hangs on such faint variations in temperature. The CMB also exposes the universe's composition. Analyses indicate a makeup of roughly 5% ordinary matter, the stuff of stars, planets, and living beings, 25% dark matter, unseen yet gravitationally present, and 70% dark energy, tied to the accelerating expansion. These proportions carry heavy implications. They suggest that most of what steers cosmic behavior is not what we can touch or see. The CMB even speaks to geometry. The pattern and scale of its temperature fluctuations imply a universe that is flat within the margin of error. Flatness means parallel lines never meet and never spread apart. It shapes how we imagine the universe's form and how its expansion unfolds, as if the basic rules of space are balanced on a narrow edge. The CMB has also fed our understanding of inflationary theory, the idea that the universe underwent a rapid expansion in the first fraction of a second after the Big Bang. The broad uniformity of the CMB across the sky supports that early exponential growth, smoothing initial irregularities into the near-even cosmos we observe now, while leaving slight variations that later became galaxies and other structures. And still, the CMB does not let the story close neatly. It has become a backdrop for probing possible physics beyond the standard model. Anomalies and unresolved features, like the cold spot or subtle mismatches in temperature fluctuations, keep pulling at the edges of what we think we understand, inviting more work and more theories that might extend current physics. As the Big Bang's afterglow faded, the universe slipped into the cosmic dark ages, a span from about 380,000 years to a billion years after its beginning. In that era, space was filled with a thick, cooling fog of hydrogen gas. It made the universe opaque, almost hidden from the kinds of light our telescopes rely on. With no stars or galaxies to light it up, this epoch sits like a silent chapter, dark and uneasy, a stretch of time when the cosmos offered almost nothing back. Yet the Dark Ages mattered. They set the conditions for the first stars and galaxies. As expansion continued, the primordial gas began to gather into clumps under gravity. Denser regions grew denser still, becoming cradles for the first stars, the population 3 stars. They were unlike the stars we see today. They were massive, brilliant, and brief. They were made almost entirely of hydrogen and helium. Inside them, nuclear reactions eventually reionized the surrounding hydrogen gas. That process pierced the opaque veil of the Dark Ages and pushed the universe into a new era of transparency and light. This transition, cosmic reionization, marked the end of the Dark Ages and prepared the way for the intricate structures we see now. The light from those first stars and galaxies began to travel outward, slowly filling the cosmos, gradually illuminating what had once been almost entirely dark. This era grips astronomers and cosmologists because it carries the earliest hints of structure and of dark matter, something that tugs on everything through gravity, yet gives nothing back to the eye. No glow, no shadow, no trace in light. Studying the cosmic Dark Ages is brutal for one simple reason: the signal is almost gone. The light is so faint it feels like the universe is refusing to testify. And yet the veil is starting to thin. Technology has sharpened, new telescopes are coming online, distant quasars and young galaxies offer fractured glimpses through the murk. The cosmic microwave background, the leftover heat of the Big Bang, still hums beneath it all. Put together, these observations begin to outline what should not be visible, as if the past is there, but only in pieces. These studies do more than describe the Dark Ages. They touch the deeper machinery that has pushed the universe from its first moments to now. When the Dark Ages ended, the cosmos did not simply brighten, It changed direction. A transformation began. The first stars and the first galaxies entered the story, and nothing could be the same afterward. This turning point arrived roughly 100 million years after the Big Bang. At first, the universe was close to uniform, a smooth ocean of hydrogen and helium, but it was never perfectly smooth. Tiny density differences existed, and as if some hidden hand could amplify a whisper into a command, dark matter may have deepened those variations, creating regions where gas was just slightly more gathered than elsewhere. In those denser pockets, gravity took over, quiet at first, then inevitable. It pulled gas inward, tightening the collapse. The clouds grew denser, hotter. Pressure rose, until the core conditions crossed a threshold that feels less like a choice and more like a trigger. Nuclear fusion ignited. The first stars were born, vast, luminous, built mostly from hydrogen and helium. Population 3 giants, larger than the stars we know, burning so fiercely their lives were short by cosmic standards. Their ignition returned light to the universe and ended the cosmic dark ages, but they did not remain lonely flames. Gravity drew them together. They clumped, merged, and gathered into the first galactic centers. Those early galaxies were smaller and less ordered than the ones around us now. Still, they were the beginnings, the seeds. From them, later spirals and ellipticals would grow. As these first stars aged, they changed the universe in another way. Fusion in their cores forged heavier elements like carbon, oxygen, and iron, things that had not existed before. When the stars died, they expelled those elements into space through supernova explosions, scattering new material into the cosmos. The building blocks for later stars, planets, and eventually life were set loose, as if the universe learned how to make more than it started with. The birth of the first stars and galaxies set off a complex chain of interactions that would steer cosmic evolution. Their radiation began to reionize the surrounding medium. The early fog started to clear. The universe became more transparent to light. This process, cosmic reionization, unfolded slowly, stretching from about 150 million to a billion years after the Big Bang. Gradual, but essential. Without it, the starlit universe we see would not look like a universe at all. And while the first stars and galaxies began to light up the cosmos, something invisible was already there, shaping where that light could appear. A scaffold you cannot see, but cannot escape. Dark matter. It makes up a huge portion of the universe's mass, yet it does not interact with electromagnetic forces. It does not emit light. It does not absorb it. It does not reflect it. To our instruments, it is nothing, and still, it holds everything. Dark matter matters because structure depends on gravity, and gravity depends on mass, whether visible or not. Galaxies and clusters form and persist the way they do because dark matter's gravity anchors them. Its presence was first inferred through what it does to visible matter. Galaxies rotate so fast that, without a large amount of unseen mass, they should fly apart. They do not. They remain bound, as if held by something that will not show itself. The clustering of galaxies tells the same uneasy story. So does the cosmic microwave background. Together they imply there is far more matter than we can directly observe. Studies estimate dark matter makes up about 85% of the universe's total matter, a number that feels less like a statistic and more like a warning about how little of reality is available to us. In the early universe, slight density fluctuations became the seeds of the first structures. Dark matter, influenced by gravity alone, began to clump within the denser regions. It formed vast halos, gravitational wells that pulled in normal, baryonic matter. Gas fell into these pits. Hydrogen and helium gathered where dark matter had already deepened the terrain. This accelerated the formation of stars and galaxies, because the halos provided the framework for gas to cool and condense. As stars formed and assembled into the first galaxies, they traced the dark matter distribution beneath them. The visible universe followed the invisible map. Over time, this produced the large-scale structure we recognize today. Galaxies and clusters woven into a cosmic web of filaments and voids, a pattern that looks almost designed, until you remember it was built on something we still cannot see. This structure, forecast by simulations that include dark matter, aligns with what we observe on the universe's largest scales with an almost unsettling precision. Dark matter's role in building cosmic structure is still being chased, still pulling at cosmology like a loose thread that won't stop unraveling. We infer it from gravity's fingerprints, yet what it actually is stays hidden, one of science's most stubborn voids. Candidates keep appearing, exotic particles like WIMPs, axions, far lighter than electrons, names that feel solid until you realize they might be shadows we invented to fill the dark. And after all the searching, nothing has been caught directly. No decisive signal, just absence. That absence keeps dark matter at the edge of both theory and experiment, where certainty thins out. Following the filaments, dark matter seems to weave through the cosmic tapestry. Star formation starts to look less like a choice and more like a consequence. Gas gathers. Cold, vast clouds of gas and dust take shape. Molecular clouds or nebulae, mostly hydrogen, a little helium, and faint traces of heavier elements, as if the universe only recently learned that complexity is possible. Inside these nebulae, denser pockets form. Sometimes dark matter's gravity helps tip the balance. Sometimes nearby supernovae disturb the calm. Sometimes gas clouds collide and something gives way. Once a dense region crosses a critical mass, gravity begins to win. Internal pressures resist, then falter. Collapse starts. The cloud contracts, and the center grows denser, hotter, as if the universe is squeezing meaning out of emptiness. It can take millions of years, slow enough to doubt it's happening at all. Yet it is the first irreversible step. In this phase, a protostar forms, a hot core, not a star yet, but no longer just a cloud, a threshold you can't unsee. As the protostar keeps drawing in material, the temperature climbs. Then, around 10 million degrees Celsius, fusion ignites. Hydrogen nuclei fuse into helium, releasing an almost violent flood of energy. That moment marks a star's birth. It also stops the collapse, forcing a fragile equilibrium. Gravity pulling inward, fusion pushing outward. A star survives by holding that balance, always one failure away from falling back into itself. How big the star becomes depends on how much mass it gathers before fusion begins. More mass comes from denser or larger clouds, and those stars live faster, burning through fuel with brutal speed. Smaller stars, like the Sun, endure longer, consuming their fuel slowly, steadily, as if longevity is just restraint written into plasma. Stars don't form alone. One molecular cloud can birth many at once, a cluster of newborn lights emerging from the same cold source. They often remain bound together for a time, stellar associations and open clusters, before gravity loosens its grip and they drift apart. Star formation from cosmic gas speaks to how restless the universe really is, and how everything seems entangled. Each birth adds to the cosmos's chemical richness, spreading elements needed for planets and, potentially, life. The life cycle of a star stretches from millions to billions of years, a long arc that keeps revealing how change is the rule, not the exception. It begins in the dense, cold cores of molecular clouds, where collapsing pockets of gas and dust become protostars, then ignite once fusion starts in their cores. From there, a star's path depends mostly on its initial mass. Smaller stars, like the Sun, enter the main sequence after birth. This is most of their lifetime. Hydrogen fuses in the core, making helium, releasing energy that prevents gravitational collapse. For a Sun-like star, this stage can last about 10 billion years. But even that stability is temporary. When hydrogen in the core runs out, fusion stops there. The core contracts under gravity, heating as it tightens. Hydrogen fusion continues in a shell around the helium-rich core, and the star's energy output rises. The outer layers expand and cool. The star becomes a red giant. In that swollen phase, it can engulf nearby planets, rewriting its solar system without asking. The final stages depend on mass. For stars up to about 8 times the Sun's mass, the core eventually sheds its outer layers, forming a glowing gas shell, a planetary nebula. The remaining core becomes a white dwarf, dense and hot, roughly Earth-sized, fading over billions of years. More massive stars, though, reach an end that is far more violent. After a star burns through its stacked layers of elements, the core gives way. It collapses. A supernova follows. For a brief moment, the blast can drown out the light of entire galaxies. In that violent flare, many heavy elements are made and thrown outward, scattered across the universe. What is left behind feels unreal in its extremes. Sometimes it is a neutron star, impossibly dense, only a few kilometers across. Sometimes, if the star was massive enough, it becomes a black hole, a region where gravity is so absolute that even light cannot get out. The life cycle of a star is not merely a timeline, it is a pillar holding up cosmic evolution. It feeds chemical complexity and nudges how galaxies form and change. And inside stellar cores, something keeps happening that has unsettled and drawn scientists for generations. Lighter matter turning into heavier matter. That transformation is nucleosynthesis, the quiet engine behind a star's gift to the cosmos. It starts simply. Hydrogen, the most common element, fuses into helium. Energy spills out. That energy becomes the light and heat we call a star, including the Sunday. But the relief of that simplicity does not last. As stars age, especially those larger than the Sun, their interiors become harsh enough to push further. Helium and other light elements fuse into heavier ones. In the core, temperature and pressure climb to staggering levels. Reaction follows reaction, building carbon, oxygen, silicon, and finally iron. Each step upward demands worse conditions, the kind found only in the biggest stellar cores or in the explosive chaos of supernovae. Carbon, for instance, forms when 3 helium nuclei fuse, a process that needs temperatures above 100 million degrees Celsius. Even saying that number does not make it feel stable. It only makes it feel inevitable. This climb ends at iron, the most stable form of nuclear matter. And here the story tilts. Fusion reaches a line it cannot cross. Unlike lighter elements, fusing iron does not release energy. It drains energy. So when a core becomes iron, it is not progress anymore. It is a warning. It is the beginning of the end. Without energy from fusion to push back against gravity, the core collapses, and for the most massive stars, a supernova erupts. In that catastrophic violence, the heaviest elements of all are formed, including gold, uranium, and plutonium. The debris is rich beyond reason. It is thrown into space, seeding the next generation of stars and planets. This recycling keeps life's ingredients from staying locked inside distant stellar hearts. They spread, they drift, they find their way everywhere. The iron in our blood, the calcium in our bones, the oxygen we breathe, all of it was forged in stars that are long gone. The connection is not poetic, it is physical, and once you see it, it is hard to feel separate again. When stars reach the end of their lives, the universe does not offer a gentle closing. The finale depends on mass, and the outcomes diverge. A star's death is not only an ending, it is the start of another turn in the cosmic cycle of matter. For stars like the Sun, the last act begins when the core runs out of hydrogen and it has all been fused into helium. The star swells into a red giant. That swelling is an attempt to regain balance. The star starts fusing helium into heavier elements, like carbon and oxygen, in the core or in shells around it. Eventually, it sheds its outer layers into space. A planetary nebula appears, brief and luminous. What remains is a hot core that cools and dims into a white dwarf, dense, Earth-sized, quiet. It can spend billions of years fading into the background, its nuclear fires fully extinguished. More massive stars do not get quiet endings. Their final phase is faster, more frantic. They run through rapid, energetic fusion reactions that build a layered interior, with iron at the center. But iron yields no energy, so pressure fails. Gravity wins. The core collapses catastrophically in seconds. That collapse triggers a supernova, among the most energetic events in the universe. It can briefly outshine entire galaxies, and it hurls the star's forged elements into space. The remnant may become a neutron star, about 20 kilometers wide yet more massive than the Sunday. Or it may become a black hole, where gravity is so strong that light cannot escape. These end-of-life events are not just spectacle, they shape the universe. The elements made and dispersed by dying stars seed the cosmos with the raw material for new stars, new planets, and potentially life itself. Supernovae, in particular, create and distribute the heavy elements we depend on, spreading iron, calcium, and carbon across the galaxy. Galaxy formation. I keep turning the idea over in my mind. Galaxies are not just scenery. They are immense gatherings of stars, gas, dust, and dark matter. And somehow, they rose out of rules that feel both clean and cruel. The story stretches across billions of years, yet it begins in a moment that still feels too bright to trust. After the Big Bang, everything was a hot, dense flood of particles. As space expanded, it cooled. Protons and electrons finally joined into neutral hydrogen. Recombination. The universe went from opaque to transparent, and light could move freely for the first time. That should feel like certainty. It does not, because it was never perfectly smooth. Tiny differences in density, faint ripples left from the beginning, were enough to tilt the future. Gravity took those slight imbalances and made them unavoidable. Regions just a bit denser pulled in more matter, then more again, growing heavier as if the universe could not stop itself. Gas clouds, mostly hydrogen, began to collapse under their own weight. Gravitational collapse. A simple phrase for something that feels like the first crack in stability. As the clouds tightened, the first stars ignited. Protogalaxies formed, plain and fragile, destined to become the complicated systems we see now. Yet gravity alone does not carry the whole burden. Dark matter sits behind the visible world, silent and unseen, refusing to emit, absorb, or reflect light, but it still pulls. It dominates the universe's matter, about 85% of it, and that fact never stops feeling unsettling. Dark matter clumped early, forming deep gravitational wells. Ordinary matter fell into them, and galaxies assembled faster, as if guided by scaffolding we cannot touch. Then there is feedback, the part that makes the process feel less like steady construction and more like interruption. Star formation and supernovae poured energy back into young galaxies. Gas heated, gas was pushed out. Cooling and collapse were slowed, not stopped, just regulated. The pace of star birth changed, and the result is the unsettling variety we try to categorize today. Spirals like the Milky Way, ellipticals, irregulars, different shapes, different histories, but none of them truly calm. And galaxies did not grow alone. In the early universe, crowded and restless, collisions and mergers were common. These encounters could reshape a galaxy and shift its star formation rate, carving new structure and feeding the growth of supermassive black holes at their centers. Even now, galaxies keep evolving, pressed by their environments, tugged by neighbors, influenced by intergalactic gas. Studying how they form and change is not just a look back in time. It is a reminder that creation, transformation, and interaction are tangled together, and the universe is held up by forces that do not ask for permission. In the wider view, galaxies appear in countless forms, billions of them, classified into a few main types that feel neat only because we insist on order: spiral, elliptical, irregular. 3 names for outcomes, shaped by formation and interaction. Spiral galaxies, like our Milky Way, show a flat disk and winding arms that reach from a central bulge. The bulge is dense with older stars. The arms wrap outward, active with star formation, rich in gas and dust, often lit by nebulae and young hot stars. The spiral pattern is thought to come from density waves moving through the disk, compressing gas and dust and triggering star birth in a repeating ripple. Elliptical galaxies feel quieter, but not in a comforting way. They have no clear arms. Their shapes run from near spherical to stretched ellipses. They contain mostly older, redder stars and very little gas or dust, leaving them poor in new star formation. Their sizes vary wildly, from giants dominating clusters to dwarfs drifting near larger neighbors. Their origins are often tied to mergers, collisions that strip away gas and smooth out structure, leaving something that looks settled only because it has lost what could change it. Irregular galaxies refuse the comfort of symmetry. They lack coherent form. They look chaotic, as if shaped by disturbance that never resolved. Yet they are rich in gas and dust, and that abundance makes them fertile for star formation, bright with the very process that other galaxies have already burned through. Irregular galaxies do not keep their shape. Gravity tugs at them, collisions batter them, their structure warps, and star formation can flare in sudden bursts. Astronomers watch them because these broken forms hint at how galaxies meet, change, and grow older. And even beyond the main labels, there are subtypes and peculiar galaxies that refuse to sit still in any neat box. Often, that refusal is born from interactions that are dynamic and sometimes violent. Lenticular galaxies sit in that uneasy middle. They carry a large central bulge and a disk, yet they lack spiral arms. They seem to hover between spiral and elliptical. This variety is not decorative. It is a warning. Cosmic evolution is complicated, and gravity, collision, and merger events keep rewriting the universe's structure. In the vast spread of the universe, galaxies are grand assemblies of stars, gas, dust, and dark matter. They appear in many forms. They are counted in the billions. We sort them into a few main types, each with its own traits and origins, as if that could hold. Spiral, elliptical, and irregular galaxies stand out. Each carries a different trace of evolution and interaction. Spiral galaxies, like the Milky Way, look flat and disc-shaped. Their arms curl outward from a central bulge. The bulge is crowded with older stars. Around it, the arms wrap in sweeping arcs. Those arms are active sites of star formation. They hold gas and dust, the raw material for new stars. Bright nebulae and young, hot stars can light them up with a clear glow. The spiral pattern is often linked to density waves moving through the galaxy. As the waves pass, they compress gas and dust. Star formation ignites in a rippling sequence. Elliptical galaxies feel different. They do not show a defined disk or spiral arms. Their shapes range from nearly spherical to stretched and elongated. They are made mostly of older, redder stars. Gas and dust are scarce. New star formation is minimal, leaving them almost barren. Elliptical galaxies also vary in size. Some are giants that dominate their local clusters. Others are dwarfs that drift like faint shadows near larger neighbors. Their formation is often tied to mergers of smaller galaxies. The merging strips away gas. What remains looks smoother, with less structure to hold on to. Irregular galaxies, true to the name, lack the coherent order seen in spirals and ellipticals. They can look chaotic, without a settled form, yet they can be rich in gas and dust, making them fertile for star formation. Their irregular shapes can come from gravitational interactions or collisions with other galaxies. The distortions arrive first, then the bursts of star formation follow. Because of that, these galaxies matter to astronomers. They often reveal how interaction and evolution actually play out. And still, beyond the broad categories, there are peculiar galaxies that defy simple classification, again and again, often shaped by the same restless and sometimes violent encounters. Lenticular galaxies return as a reminder: a big central bulge, a disk, no spiral arms, a category between spiral and elliptical. The diversity does not resolve into comfort. It underscores the complexity of cosmic evolution and the influence of gravity, collision, and merger events in shaping the universe's structure. The story of the Milky Way's formation stretches across billions of years. It pulls together gravity, the mystery of dark matter, and the life cycle of stars. At the center is hierarchical assembly. Smaller components merge into larger structures. That principle runs beneath how galaxies evolve across the universe. Our Milky Way, a barred spiral galaxy with vast swirling arms around a luminous core, began about 13.6 billion years ago, not long after the Big Bang. The early universe was a cosmic soup of hydrogen, helium, and traces of lithium. Slight irregularities in density began to gather under the relentless pull of gravity, and somewhere in that gathering, the enigmatic presence of dark matter may have been shaping what could form, even as the full picture refused to stay solid. Denser regions drew in more matter, swelling into the first protogalaxies, fragile precursors of today's galaxies. As they drifted and circled one another, gravity quietly tightened its grip. Collisions followed, mergers stacked upon mergers. With each one, the young Milky Way became larger, more tangled, less simple than before. Dark matter, unseen but unavoidable, shaped this growth from the shadows, steering gas and stars into patterns no one could directly observe. The disk where our solar system now sits emerged slowly, not by design, but through motion and persistence. Gas settled into the galactic plane, spiraled inward, and began to ignite new stars. Over immense spans of time, those stars forged heavier elements and scattered them back into the galaxy, laying the raw groundwork for planets and, eventually, life. At the center, the bulge formed early, dense and crowded, holding many of the galaxy's oldest stars. Around it stretched the halo, thin and elusive, filled with globular clusters and the broken remains of smaller galaxies that did not survive their encounter with the Milky Way. The spiral arms traced restless waves moving through the disk. Where those waves compressed gas and dust, stars were born, briefly lighting the arms across vast distances. Growth never truly stopped. Gas continued to fall in. Other galaxies were absorbed. Change became the only constant. Ahead lies another turning point. In roughly 4 billion years, the Milky Way is expected to collide with the Andromeda Galaxy. It will not be a gentle meeting. Both systems will be reshaped, erased, and recombined into something larger, something unfamiliar. Across the universe, supermassive black holes sit at the cores of galaxies, including our own, acting as silent centers of control. With masses millions or billions of times that of the Sun, they distort everything around them. Their presence ties the fate of stars, gas, and dust to a single, overwhelming gravity. The connection between these black holes and their host galaxies runs deeper than once assumed. The mass of a central black hole tracks closely with the properties of the galactic bulge, hinting that neither grows alone. As black holes feed, they release immense energy. Radiation and outflows surge outward, heating nearby gas or driving it away entirely. Star formation slows. Sometimes it stops. This feedback prevents galaxies from consuming themselves too quickly, forcing a longer, uneasy balance. The same energy can leave surrounding gas too hot to collapse, further stalling the birth of new stars. In this way, black holes quietly limit how large and dense galaxies can become. Their gravity also reshapes galactic centers. Stellar orbits bend and twist under its influence. In rare moments, stars are flung outward at extreme speeds, expelled from their home galaxy altogether. These events reveal how unstable and violent galactic cores can be. How supermassive black holes first formed remains uncertain. They may begin small, growing through steady feeding and through mergers with other black holes. Even now, the full story is incomplete, and the structure we rely on feels far less solid than it once seemed. This growth is believed to unfold alongside the rise of the host galaxy itself. The two cannot be cleanly separated. Galaxies and their central black holes appear bound in a shared, uneasy evolution. The Milky Way, our home galaxy, feels stable only from a distance. Its structure is vast and intricate, almost too ordered to trust. Seen as a giant spiral, it is built from distinct parts, each necessary, each fragile. At the center sits a swollen core of stars. Wrapped inside it is a supermassive black hole, Sagittarius A. It does not shine, it does not announce itself, yet its gravity quietly governs the motion of the entire galaxy. The surrounding bulge is dense, crowded with stars that formed long ago. Many are ancient. Their presence hints at an early era we can no longer see clearly, only infer. Beyond the bulge stretches the disk. It spans nearly 100,000 light-years. It holds stars, planets, gas, and dust, all mixed into a thin, restless plane. The disk is uneven. Spiral arms cut through it, regions where matter compresses and stars are born in bursts of light and heat. These arms carry familiar names: Perseus, Sagittarius. Their shapes are thought to arise from density waves that sweep through the disk, squeezing gas until new stars ignite. Somewhere within this structure lies the Sunday. It drifts inside a smaller feature, the Orion Spur, about 27,000 light-years from the center. From here, we observe the galaxy, but never completely. Dust and gas block our view. Large portions of the Milky Way remain hidden, leaving gaps in our understanding that refuse to close. Surrounding everything is the halo. It is spherical and diffuse, populated by stars and globular clusters that orbit far from the disk. These clusters are tightly bound and extremely old. They are remnants of the galaxy's earliest stages, carrying faint records of how the Milky Way came together. The halo also holds most of the galaxy's dark matter. It cannot be seen, it cannot be touched. Yet its gravity shapes the motion of stars and gas, silently holding the galaxy in place. Without it, the structure would not endure. The Milky Way is not alone. It is encircled by smaller satellite galaxies, including the large and small Magellanic Clouds. They orbit slowly, locked in long gravitational exchanges. Over billions of years, these interactions reshape them. Some may eventually dissolve into the Milky Way itself. The age of our galaxy deepens this unease. Evidence suggests the Milky Way is about 13.6 billion years old. It formed soon after the Big Bang, which occurred roughly 13.8 billion years ago. This places our galaxy among the older structures in the universe, born when cosmic conditions were still unstable. Estimating this age requires assembling fragments of evidence. One path comes from studying the oldest stars. Their chemical makeup reveals how early they formed. These stars contain fewer heavy elements because such elements only accumulated after generations of stellar death. Many of these ancient stars reside in the halo and in globular clusters. Their ages trace the Milky Way's earliest growth, though never with absolute certainty. Another approach relies on the age of the universe itself. Measurements of the cosmic microwave background and the expansion of space set the outer limits. When these values align with stellar ages, a consistent picture emerges. The Milky Way formed early, almost uncomfortably close to the beginning. This age tells more than a number. It implies a long, uneven history of accumulation, star formation, and mergers. The galaxy grew slowly, piece by piece, across immense time. What feels permanent now is the result of processes still unfolding, still capable of change. The Milky Way took shape slowly, guided by forces we cannot see. Dark matter threads through the galaxy, steering its growth into the spiral we now recognize. When we speak of the galaxy's age, scale begins to slip, time stretches. The Sun, at 4.6 billion years old, is not ancient here. It is late arriving. Star formation never really stopped. The galaxy is still unsettled, still changing. The galactic center draws attention for a reason. It feels heavy with meaning. Buried deep in the Milky Way, about 27,000 light-years away, it marks the dense and luminous core of our galaxy. At its heart lies Sagittarius A, a supermassive black hole. Everything seems to lean toward it. With a mass around 4 million times that of the Sun, Skure A holds the galaxy together through gravity alone. The vast spiral structure bends around this invisible weight. Nearby, stars and gas crowd into a tight, restless space. Nothing there feels calm or sparse. The stellar population is strangely mixed. Young, blue stars burn intensely beside ancient, cooler stars that have circled the center for billions of years. This should not happen. So close to a black hole, tidal forces ought to destroy the raw material needed for starbirth. Yet the young stars remain. Their presence quietly undermines what we expect. It suggests that star formation near the galactic center follows different rules. Around them drift thick clouds of gas and dust. Some are falling inward towards Skure A, others may still be giving rise to stars. Magnetic filaments cut through the region. Radiation pours out as matter spirals into the black hole. The environment is volatile. Flares erupt. Energy is released in bursts that hint at violent interactions between Skr A and its surroundings. Each event offers a glimpse into extreme physics, though never a full explanation. Seeing this region is difficult. Interstellar dust blocks visible light, hiding the center from direct view. Astronomers work around this barrier. Radio, infrared, and X-ray observations push through the darkness. Piece by piece, the structure emerges. These observations confirm the black hole's presence and reveal how deeply it shapes its environment. The Milky Way does not stand alone. It is surrounded by smaller satellite galaxies, held close by gravity's quiet pull. These relationships are not gentle. They are active and sometimes disruptive. Over time, they leave marks on the galaxy's structure and evolution. The large and small Magellanic Clouds are among the most prominent companions. Rich in gas and dust, they move in a slow gravitational dance with the Milky Way. As they orbit, tidal forces strip gas from them. This material drifts into the Milky Way, adding to the supply from which new stars can form. The influence flows both ways. The pull of these satellites has subtly warped the Milky Way's disk, a quiet sign that no galaxy is truly self-contained. These encounters also create tidal streams. Long, thin trails of stars and gas stretch across space, remnants of smaller galaxies pulled apart or fully absorbed. Some streams trace back to satellites that no longer exist as separate systems. They preserve a fragile record of past collisions. The Sagittarius dwarf spheroidal galaxy stands as another stark reminder of how these interactions unfold. This small galaxy is being slowly consumed by the Milky Way. Its structure is unraveling under relentless gravitational strain. Long streams of stars now loop around our galaxy, quiet evidence of a system coming apart. What remains tells a deeper truth. Galaxies do not stand still. They erode, absorb, and erase one another. These encounters are not accidents of cosmic violence. They are how galaxies change. Each absorbed satellite delivers new gas, quietly feeding future stars. Each interaction stirs matter inside the Milky Way, reshaping its balance and motion. Growth comes through loss, order through disruption. Looking ahead, the Milky Way offers no sense of permanence. Astronomers peer forward using simulations and distant light, and what they see is instability. Gravity never rests. Star formation continues. Collisions wait their turn. The galaxy we recognize is temporary. The most inevitable event is the encounter with Andromeda. It is distant, yet approaching. About 2.5 million light-years away, closing in at roughly 110 kilometers per second. In about 4 billion years, the sky itself will be transformed. Nothing familiar will remain untouched. As the galaxies draw together, gravity will tighten its grip. Spiral forms will stretch and distort. Eventually, they will merge into a single elliptical galaxy, often given light-hearted names that fail to capture the scale of the event. This is not instant destruction. It is a slow, disorienting rearrangement. Stars rarely collide, but their paths will be rewritten. Some stars will be thrown into new orbits. Others may be expelled entirely. Gas clouds will not be so lucky. They will crash together, igniting bursts of star formation that briefly illuminate the chaos. At the center, the supermassive black holes of both galaxies will dominate the aftermath. These black holes will spiral inward over time. When they finally merge, enormous energy will be released. Space-time itself may tremble. Even then, the transformation does not end. The galaxy will continue to age, carried forward by the quiet decay of its stars. As stars exhaust their fuel, they change form or explode. Massive ones end in supernovae. Smaller ones shed their outer layers and fade. Over trillions of years, the galaxy will dim. White dwarfs, neutron stars, and black holes will outnumber shining suns. Beyond the galaxy, the universe keeps expanding. Distant galaxies slip away, disappearing from view. From inside the Milky Way, space will look emptier, quieter, almost abandoned. Only nearby galaxies will remain bound together. A small island of matter adrift in accelerating darkness. The story of the solar system begins inside this unstable setting. About 4.6 billion years ago, a cloud of gas and dust collapsed in a shadowed region of the Milky Way. Gravity pulled it inward. A shockwave, likely from a nearby supernova, may have pushed it past the point of return. As the cloud fell inward, it began to spin. It flattened into a disk. Material thickened at the center. A protostar formed, growing hotter and denser until nuclear fusion ignited. The sun was born, not in calm, but in collapse. Around it, debris remained. Dust collided. Fragments stuck together. Slowly, unevenly, larger bodies emerged. Close to the sun, heat allowed only metals and silicates to survive. Rocky planets took shape. Mercury, Venus, Earth, Mars. Earth alone would later host life. Farther out, cold changed the rules. Ice could persist. Giant planets formed, pulling in gas and frozen compounds. Jupiter and Saturn grew massive with hydrogen and helium. Uranus and Neptune gathered water, ammonia, and methane ice. The solar system settled into a fragile order, shaped by chance, violence, and time. Nothing about this process was stable. Nothing about it was guaranteed. The far edges of the solar system gave rise to the Kuiper Belt and the Oort cloud, vast, cold reservoirs of icy bodies, comets, and dwarf planets like Pluto. These objects are leftovers from the beginning, preserved, barely altered. They feel like frozen memories of a system that never fully settled. One presence looms over this history: Jupiter. Its massive gravity bent paths and rewrote destinies. Some objects were pulled inward, lost to the Sunday. Others were hurled outward, abandoned to deep space. Nothing moved freely. Everything was pushed or restrained. Over billions of years, the solar system never stood still. Orbits shifted, worlds collided, order emerged through violence. The late heavy bombardment marks this unrest. Around 3.8 billion years ago, impacts surged. Comets and asteroids struck with relentless force. The scars remain. To understand how this system formed, scientists piece together fragments, observations, simulations, meteorites. Each offers evidence, but never certainty. Together, they hint at origins and suggest that other planetary systems may have formed through similar turmoil. The Milky Way itself was never a passive backdrop. It shaped the conditions from the start. Its immense clouds of gas and dust, its gravity, its long cycle of stellar birth and death, all of it set the stage for the Sun and everything bound to it, about 4.6 billion years ago. At the core of this story lies the interstellar medium, thin, vast, mostly hydrogen and helium, mixed with dust, enriched slowly by generations of dying stars. Supernovae scattered heavy elements into space: carbon, oxygen, iron. Without them, rocky planets could not form. Life would not have had a chance. The galaxy's gravity mattered too. Its spiral arms swept through space, compressing gas and dust, triggering new stars. Somewhere in this restless motion, the solar system took shape. Inside a dense molecular cloud, conditions balanced on a knife edge, just enough for the solar nebula to collapse and hold together. The Milky Way's chemical history set limits. It decided what could form. Close to the young sun, only heat-resistant materials survived. Mercury, Venus, Earth, Mars. Farther out, cold ruled. Gas and ice gathered. Giants took shape where volatility was allowed. Location mattered. The solar system formed in the Orion Arm. Quiet. Removed from the galaxy's violent core. Fewer disruptions. Less radiation. A rare calm. This stability allowed Earth to persist, and eventually, to observe the universe that shaped it. Earth's formation unfolded within the solar nebula, a slow, chaotic process. Gravity pulled the cloud inward, rotation flattened it into a disk. At the center, the sun ignited. Light and heat spread outward, changing everything. Far from that heat, dust and ice collided, stuck, broke apart, stuck again. Small clumps grew larger. Planetesimals emerged, Drawn together by gravity, they collided endlessly. Accretion took over. The inner planets began to form. Earth grew fast, but not gently. Bombarded, scarred, absorbing material in constant impacts. Within tens of millions of years, it reached much of its size, not finished, never truly stable. A planet born from collapse, shaped by chance, in a system that was never as solid as it seems. As Earth grew, its interior began to burn from within. Collisions released energy, radioactive elements decayed in silence. Heat built up, the young planet softened, then partially melted. Matter sank and separated. A heavy metallic core formed. Above it, a silicate mantle. On top, a fragile crust. This separation mattered more than it first appeared. The core's motion gave rise to a magnetic field, an invisible shield. Without it, radiation would have scoured the surface. At the same time, heat tore gases from solid rock. Volcanoes exhaled relentlessly. Water vapor escaped. Carbon dioxide followed. Methane, ammonia. An atmosphere took shape, harsh and alien, nothing like the air we trust today. As cooling began, the sky changed. Water vapor condensed. Rain fell for ages. Basins filled. Oceans spread across the surface. Liquid water appeared, quietly essential. Along with Earth's size, its orbit, and its magnetic shield, conditions stabilized. Not safe, but possible. Over billions of years, the surface and the air kept changing. Life emerged, and then altered everything. Photosynthetic organisms released oxygen. Slowly, the atmosphere transformed. Oxygen accumulated. The planet became tolerable for complexity. Biology and geology intertwined, reshaping Earth again and again until it resembled the living world we now inhabit. Life on Earth, in all its diversity, did not arrive by accident alone. It arose from a rare convergence of conditions unfolding over immense time. The planet's position, its air, its oceans, all aligned just enough to sustain life. One condition stands out: Earth's location in the solar system. The so-called Goldilocks zone, not too close to burn, not too far to freeze, a narrow margin, little room for error. Within this zone, liquid water persisted, a fragile requirement. The atmosphere, born from volcanic gases like water vapor, carbon dioxide, and ammonia, did not remain the same. Over time, it shifted. Photosynthetic life converted light, water, and carbon dioxide into oxygen. The air changed again. Rising oxygen supported new life forms. It also created the ozone layer, another thin defense, blocking lethal ultraviolet radiation. Beneath it, Earth's magnetic field continued its work. Generated by molten iron deep within the outer core, it deflected solar and cosmic radiation. Without it, the atmosphere could have been stripped away. Life would have been exposed. This shield preserved stability. But stability was never stillness. Geological activity persisted. Plate tectonics reshaped the surface. Continents collided and separated. Ocean basins opened. Carbon cycled through rock and air, regulating temperature over deep time. Minerals and nutrients spread unevenly, creating varied habitats. Water existed in solid, liquid, and gas forms, an unusual balance. Water dissolved substances, carried reactions, enabled complexity. Its properties quietly governed chemistry and life alike. The moon played its part. By stabilizing Earth's axial tilt, it calmed the climate. Seasons remained moderate. Extremes were limited. Ecosystems had time to grow, adapt, and persist. Then there is dark energy, a name that unsettles. It dominates the cosmos, shaping its fate. About 68% of the universe belongs to it. It drives expansion, not slowing, but accelerating. A revelation that overturned expectation in the late 1990s. Observations of distant supernovae revealed the truth. Galaxies were not easing apart, they were rushing away faster over time. Gravity was not winning, the universe was not settling. It was pulling itself open, faster and faster, under the influence of something unseen. The acceleration pointed to something unsettling. An unknown energy spread through all of space, pushing outward, quietly overpowering gravity on the largest scales. We call it dark energy, but the name explains nothing. Its nature remains unclear, and that uncertainty sits at the core of modern physics. What we do see is its effect. Space expands faster and faster, structures change, galaxies form and evolve under its pressure. Without it, the universe might have fallen back into itself or stretched outward at a crawl, leaving a cosmos unrecognizable to us. One leading idea is the cosmological constant, first introduced by Albert Einstein. It describes a steady energy embedded in space itself, unchanging over time. Another possibility feels less stable. Dark energy could be a dynamic field shifting across space and time. If so, the rate of expansion may not be fixed, and the future may not be either. Its presence forces us to confront the universe's end. If dark energy stays constant or grows stronger, expansion never stops. Galaxies drift apart. Space grows colder, emptier. If its repulsive force intensifies further, everything could be torn apart in a final unraveling. Galaxies, stars, even atoms pulled beyond cohesion. To understand dark energy is to question the foundations of physics itself, because current laws strain to contain it. Scientists search for answers in the cosmic microwave background, in the distribution of galaxies, in distant supernovae, and in experiments probing space and energy. Yet even as we observe, the universe continues to change. Galaxies are not fixed monuments. They evolve, slowly and relentlessly, over billions of years, shaped by forces beyond human intuition. Understanding that evolution feels essential, as if it reveals how the universe builds and dismantles itself. A galaxy's fate depends on its mass, its surroundings, and its encounters with others. In the early universe, galaxies began as small protogalaxies. They grew by pulling in gas and merging with one another. From this long process emerged the variety we see today: spirals, ellipticals, irregular forms, each carrying a different history. In spiral galaxies, star formation defines their evolution. Their arms, dense with gas and dust, give birth to new stars through gravitational collapse. Over time, gas is consumed or expelled by supernovae. Star formation slows, the light shifts. Older, redder stars begin to dominate, and the galaxy ages before our eyes, though far too slowly to notice. Elliptical galaxies often arise from mergers. These violent events ignite brief surges of star formation as gas clouds collide, then scatter and heat the remaining gas, leaving little behind to form new stars. What remains is an older population, redder, quieter, with far less raw material for renewal. Interactions between galaxies drive further change. Mergers and close passes reshape structure and alter star formation rates. When galaxies of similar size collide, spiral patterns dissolve, and a larger elliptical galaxy can emerge after a short, intense burst of stellar birth. Gravitational encounters can stretch galaxies into distorted forms, leaving tidal tails and bridges as evidence of past violence. Internal processes deepen the transformation. Supernovae inject energy into interstellar gas, heating it, pushing it outward, suppressing future star formation. Active galactic nuclei, fueled by matter falling into supermassive black holes, can expel vast amounts of gas, quietly starving a galaxy of its future stars. As galaxies grow older, their star formation fades, their populations redden. Environment accelerates this decline. In dense regions like galaxy clusters, interactions are frequent, gas is stripped away, and evolution quickens. The universe keeps moving forward, but the structures within it slowly lose their vitality, leaving behind a cosmos that feels increasingly fragile and uncertain. Galaxy collisions are not rare accidents. They are woven into the universe itself, vast, slow, and relentless. These encounters unfold over hundreds of millions of years, reshaping galaxies from the inside out. They bend structure, disturb order, and awaken storms of starbirth. What looks stable from afar is quietly being undone. When galaxies collide, gravity takes control. Shapes stretch and warp. Order dissolves. Gas, dust, and stars are pulled into unfamiliar paths. Tidal tails emerge. Rings and bridges form. Nothing stays where it was. Even though stars rarely crash into one another, the system as a whole is violently rearranged. The galaxy survives, but it is no longer the same. One of the most unsettling outcomes is the starburst. As galaxies merge, gas clouds are squeezed beyond balance. Star formation erupts. Millions of stars ignite in a short cosmic moment. The galaxy brightens, then ages faster. Its composition shifts. Heavier elements are forged, setting the stage for futures that did not exist before. Creation here feels rushed, almost desperate. At the cause, something darker happens. Central black holes drift closer as their galaxies merge. Eventually, they collide. Energy floods the surrounding space. Star formation can be throttled or triggered again. Even the heart of a galaxy is not secure. Power concentrates, then reshapes everything around it. These collisions are also believed to erase structure entirely. Spiral galaxies lose their arms. Motion becomes randomized. What remains is smoother, quieter, an elliptical galaxy, not refined, but stripped. Many see these forms as the aftermath of repeated mergers, where identity has been mixed away. On the larger scale, this process never stops. Galaxies grow by consuming smaller ones. This hierarchy has shaped the universe since its earliest moments. Clusters and superclusters bear the scars of constant assembly. The cosmos is not settling, it is still rearranging itself. Galaxy collisions reveal an uncomfortable truth. The universe is dynamic, unstable, and indifferent to permanence. Through them, astronomers glimpse dark matter at work, gravity at its most patient, and change as the only constant. Simulations and observations trace not just the past, but what waits ahead. Even the Milky Way is not spared. It is already falling toward Andromeda. In about 4 billion years, they will merge. Looking further ahead is even more unsettling. Predicting the universe's fate sits at the core of cosmology, yet certainty slips away. The equations are sound, the answers are not. Dark matter, gravity, and especially dark energy complicate everything. Dark energy now dominates the universe. If it remains unchanged, expansion never stops. Galaxies drift apart faster and faster. Star formation fades as gas runs out. The universe cools as it stretches. Trillions of years pass. Stars burn out. What remains are white dwarfs, neutron stars, and black holes. Even these do not last forever. Black holes slowly evaporate. The universe approaches silence, cold, dark, empty. But this is not the only possibility. If dark energy grows stronger, expansion turns violent. In the Big Rip, it overwhelms every force. Galaxies are torn apart. Stars unravel. Planets disintegrate. Even atoms fail. Structure itself is erased. There is also the opposite fear. If matter is sufficient to halt expansion, the universe could collapse. The Big Crunch would reverse everything. Space contracts, heat rises, all paths lead back inward, a mirror of the Big Bang. Some theories go further. In the Big Bounce, collapse does not end the story. A crunch becomes a beginning. Expansion follows again, then collapse, then rebirth. A cycle without memory. This idea leans on quantum gravity and remains uncertain, suspended between mathematics and imagination. What becomes clear is this: the universe offers no stable ending, only scenarios, only tension. The future is not written, and whatever comes, it will not preserve the world as we know it. Predicting the future of the universe means confronting the fate of its structures. Galaxies will drift and deform. Stars will burn through their fuel and fall silent. Black holes will come to rule the cosmic stage, only to fade as well, slowly evaporating through Hawking radiation if time stretches far enough. What feels permanent is not. These futures rest on what we think we know now, on theories and observations that still feel incomplete. As our understanding grows, especially of dark energy and dark matter, these predictions may shift again. Nothing is settled. Yet these projections reveal a universe in constant motion, unstable and unfinished, shaped by questions we cannot stop asking. Observational astronomy begins with this unease. Astronomers reach into the vastness using instruments far beyond anything familiar. Not backyard telescopes, but massive machines built to catch the weakest traces of light. Some stand across the Earth. Others float beyond the atmosphere, removed from the planet that distorts our view. The light they collect is ancient. It travels billions of years before reaching us. It is more than illumination. It carries memory. By breaking this light apart, scientists read its hidden structure, composition, distance, age, motion, all encoded in fragile signals. Spectroscopy makes this possible. Light is split into colors, like sunlight through a prism. Each wavelength points to specific elements. Each line marks a presence far away. When these lines shift toward red or blue, they reveal motion away from us, toward us, faster than intuition allows. This shift, rooted in the Doppler effect, unsettled our picture of reality. The redshift of distant galaxies exposed an expanding universe, a discovery that fractured old assumptions and reshaped cosmology itself. Technology pushed the boundary further. The Hubble Space Telescope sent back images sharp enough to unsettle the imagination. Distant galaxies appeared structured, delicate, real. Its successor, the James Webb Space Telescope, looks deeper still toward the first galaxies formed after the Big Bang. Free from atmospheric interference, these observatories see with unsettling clarity. Other instruments listen instead of look. Radio telescopes capture waves invisible to the eye. They reveal a different universe, one where the faint glow of cosmic microwave background radiation lingers, the afterimage of the Big Bang itself, a quiet reminder of an origin we cannot escape. When observations across all wavelengths are combined, the picture grows richer and more unstable. Radio to gamma rays, each layer adds complexity. Quasars, pulsars, signals once unknown, now reshape our understanding of cosmic evolution. Behind these discoveries stand quieter technologies. Adaptive optics bends Earth's interference back on itself. Atmospheric blur is corrected in real time. Ground-based telescopes begin to rival those in space. Details emerge where there was once distortion. Interferometry goes further. Light from multiple telescopes is merged into one image. Distance becomes resolution. Separation becomes strength. Arrays like the VLT and ALMA turn vast spaces into single instruments. They expose star birth, planetary formation, and galactic structure with precision once thought unreachable. The more we see, the less solid the universe feels. Clarity does not bring certainty. It brings awareness of how fragile our understanding truly is. Radio astronomy remains a pillar in our attempt to grasp the galaxy. It does not look at light the eye can see. It listens to radio waves released by distant objects. That difference matters. It exposes things that hide from sight. The cosmic microwave background radiation, echoes of the Big Bang, fast radio bursts with no clear origin. Each signal feels like a fracture in what we thought was solid. The square-kilometer array is meant to change everything. It aims to be the largest radio telescope ever built. It reaches back toward the earliest eras of the universe. It traces how galaxies are spread across space. The promise is vast. So is the unease that comes with seeing more than we expected. Space missions add to this quiet disruption. Satellites have become unavoidable witnesses. Gaia is charting the positions and motions of billions of stars in the Milky Way. The data redraws the structure of our galaxy, its formation, its slow evolution. The map grows sharper while certainty fades. At the same time, Kepler and TESS search for exoplanets, worlds circling stars far beyond our system. Each detection hints at life or at emptiness. Either way, the question deepens. Computational astronomy now sits at the center of this effort. The data is overwhelming. Machines are needed to see patterns we cannot. Models and simulations test ideas about galaxy formation, about black holes, about cosmic evolution. They let us explore outcomes that once felt impossible. Yet the more we simulate, the less final anything appears. Telescopes themselves tell a story of human reach. They push our vision far beyond Earth. They collect and magnify faint light from objects that barely exist to us. Optics governs this process. Light behaves, or seems to. Two main designs persist: refracting and reflecting. Refracting telescopes rely on lenses. Light enters from a distant star. It passes through the objective lens at the front. The lens bends the light toward a focal point. There the rays meet. An image forms. The eyepiece magnifies it. The larger the lens, the more light is gathered. Faint objects emerge, slowly, never completely. Reflecting telescopes use mirrors instead. A large curved mirror sits at the base. It reflects incoming light upward. Before the light settles, a smaller mirror redirects it. The image reaches an eyepiece or a detector. This design avoids chromatic aberration. Colors no longer pull apart, at least not as much as before. Modern telescopes go further. Adaptive optics attempts to correct the atmosphere itself. Mirrors shift in real time. Distortions are measured and countered. Reference stars or artificial lasers guide the process. Images sharpen. The sky resists less, but it never fully yields. Magnification is not everything. Resolving power matters just as much. It defines how close two objects can be and still remain distinct. Diameter controls this. Larger mirrors reveal finer detail, or reveal how much detail we still miss. The past century stands apart in astronomical discovery. Each finding strips away another layer of comfort. Telescopes and technology have altered not only knowledge but expectation. One discovery changed everything: the expansion of the universe. Distant galaxies show redshift. They are all moving away. In every direction, the implication is unavoidable. This led to the Big Bang Theory. The universe began in a dense, hot state. It has been expanding ever since. The idea emerged in the 1920s. It reshaped how we see cosmic time. Motion replaced stillness. Growth replaced permanence. In 1965, the cosmic microwave background radiation was found. A faint glow, almost uniform. It is the afterglow of the universe in its infancy. A view from just 380,000 years after the beginning, before stars, before galaxies. Its discovery confirmed a hot and dense origin. Expansion was no longer abstract. Another turning point followed. The first observation of a black hole. Its existence had been predicted earlier, but in 1971, Cygnus X1 was identified. A theoretical shadow became an observed presence, something unseen yet undeniable. From that moment, the universe felt less stable and far less forgiving. This finding marked a disturbing leap in how we perceive the universe's most elusive objects. Places where gravity tightens its grip until even light is erased. At the same time, the search for exoplanets began to unsettle old assumptions. Worlds beyond our solar system were no longer hypothetical. In 1992, planets were found orbiting a pulsar. In 1995, another circled a star much like our own. Astronomy quietly crossed a threshold. Since then, exoplanets have multiplied into the thousands. Each one strains our understanding of how planetary systems form. Order feels less guaranteed. Familiar patterns no longer hold. The question of life beyond Earth stops feeling distant and starts feeling unavoidable. The Hubble Space Telescope, launched in 1990, deepened this unease. It reshaped our sense of cosmic time. It exposed dark energy, an unknown force pushing the universe apart faster and faster. It revealed galaxies, stars, and planets so remote they feel almost unreal. Then came gravitational waves, subtle tremors in space-time itself, born from violent mergers of black holes. Detected in 2015, they confirmed a long-standing prediction of general relativity. More unsettling, they offered a way to observe events that light can never show us. Behind all of this stands theoretical astrophysics. Models form the fragile framework holding our understanding together. They reach where observation cannot. They hover between what we see and what might exist. Built from mathematics and physics, they attempt to impose structure on a universe that resists it. The standard model of particle physics is one such foundation. It maps the particles and forces that make reality possible. It even foretold the Higgs boson, found in 2012. That discovery revealed how particles acquire mass. A triumph, yes, but also a reminder that reality often waits to be proven. General relativity plays a similar role on cosmic scales. Gravity is no longer a simple pull. It is space-time bending under mass and energy. Light curves, orbits shift, black holes emerge. These predictions were once abstract. Now they are observed facts. This theory also underpins our understanding of cosmic expansion and made gravitational waves inevitable long before we could detect them. On larger scales still, the lambda CDM model tries to explain the universe as a whole: dark matter, dark energy, galaxy formation, background radiation, accelerating expansion. It holds together, but uneasily. Through simulations, we reconstruct the universe from moments after the Big Bang to now. We watch galaxies cluster, structures take shape, yet much remains unseen. Inflation theory reaches further back still, proposing a sudden expansion to explain the universe's eerie uniformity. Evidence remains indirect. The fit is persuasive, but not final. Theory and observation push against each other. Predictions guide instruments, discoveries strain expectations, models bend, break, or evolve. Understanding advances, but certainty does not. The universe reveals more, and with each revelation, it feels less stable than before. This quiet partnership keeps cosmology moving forward, yet it never feels final. Our understanding sharpens, then slips again. Simulations become a kind of digital universe, a fragile copy where we can touch what reality denies us. Inside computers, scientists wander through cosmic processes that no physical experiment could ever reach. These simulations are not simple tools, they are vast constructions of code, built to imitate galaxies, stars, planets, and distant events as they change over time. When the laws of physics and starting conditions are fed into them, a virtual cosmos begins to unfold. We watch events happen that we can never witness directly. It feels like seeing truth through glass. Their strength lies in scale. Space is too large, time is too long. Simulations absorb this immensity and hold it still, just long enough to study. Galaxy formation, stretching across billions of years, can be replayed and reshaped. Gravity pulls, gas flows, stars ignite, explosions and massive black holes push back. Order forms, then fractures. Within these digital worlds, parameters can be altered. Dark matter density shifts. Star formation speeds up or slows down. Each change bends the outcome. From this, scientists infer how our own galaxy and its neighbors emerged, and how they may unravel in the future. Nothing feels fixed. Simulations also probe the structure of the universe itself. The cosmic web appears as a vast lattice of dark matter, its filaments holding galaxies and clusters like fragile knots. This structure exists mostly in theory, yet simulations give it shape. When these shapes are compared with telescope data, ideas about dark matter and cosmic forces are revised. Confidence rises, then falters. In studies of planet formation and the search for life beyond Earth, simulations open another uncertain window. They trace how planets gather around stars, how atmospheres take form, how conditions might allow life to persist. They hint at signals future missions might find. These models quietly guide the design of telescopes and surveys, even as doubt lingers beneath every assumption. Simulations also confront the universe at its most violent. Supernovae erupt, black holes collide, galaxies crash together and slowly merge. Within models, these events can be examined in detail. From them come predictions. Gravitational waves, new elements forged in stellar death, the slow choreography of merging galaxies. Observations later confirm or unsettle these forecasts. At their core, simulations stand between theory and observation. They promise control in a universe that resists it. They let scientists revisit the past, inspect the present, and gesture toward the future. Each step forward exposes how much remains uncertain. Through these virtual universes, we gain more than answers. we gain proximity, a sense that the cosmos can almost be grasped, even as it slips away. Modeling galaxy formation embodies this tension. It blends careful calculation with uneasy imagination, offering a view into the birth of immense structures that still refuse to be fully known. These models rely on the laws of physics to recreate the tangled flow of matter and energy. They begin shortly after the Big Bang and move forward through deep time. Galaxies appear, evolve, distort. What emerges feels plausible, yet never complete. Many forces shape this process. Dark matter distributions guide gravity. Gas cools and collapses into stars. Black holes grow at galactic centers. Stellar winds and explosions push material outward, restraining further growth. Balance is temporary. Instability is constant. To capture this, astrophysicists combine theory with numerical simulation. Inside supercomputers, particles stand in for dark matter, gas, and stars. Equations of gravity, thermodynamics, and fluid motion govern their interactions. By changing initial conditions and physical assumptions, outcomes diverge. Each result is measured against telescope data, testing how fragile the model truly is. Dark matter sits at the center of this effort. It cannot be seen. It does not interact with light, yet its gravity dominates. Roughly 85% of the universe's matter hides in this form, shaping galaxies from the shadows. It provides the unseen framework on which everything visible depends, reminding us that most of the cosmos remains beyond direct reach. In simulations, the early universe is reconstructed from the faint pattern left in the cosmic microwave background, a fragile snapshot. Matter only 380,000 years after the beginning. From this imprint, dark matter is placed, then released into time. As gravity acts, it gathers. Slowly, inevitably, dense knots emerge. Dark matter halos take shape. Gas drifts inward. It cools. It collapses. Stars ignite. Galaxies appear. Yet this growth is never stable. Explosions from dying stars and fierce stellar winds push back. Gas is expelled. Star formation slows. The models must account for this struggle, a constant tension between creation and loss. These simulations are never finished. New observations arrive. Old assumptions weaken. Distant galaxies reveal their younger selves, billions of years in the past. Each glimpse becomes a test. Some models endure, others fracture. Understanding advances, but certainty does not. Despite progress, deep fractures remain in our picture of the universe. Questions persist, uncomfortable ones. Dark matter stands among the most troubling. It dominates the universe's matter, yet remains unseen. It gives off no light. It takes in none. We sense it only through gravity. Its substance is unknown, its identity unresolved. Possible forms have been suggested, none confirmed. Decades of searching have yielded silence. The absence grows heavier with time. Dark energy deepens the unease. It outweighs everything else. It drives the universe to expand faster, not slower. This single discovery overturned what once felt secure. We know its effect, not its nature. Its behavior could decide the fate of everything. Still, it remains out of reach. Even the universe's expansion rate refuses to settle. Different measurements disagree. The gap persists. No simple explanation holds. The tension hints at something missing, something unaccounted for. Perhaps new physics. Perhaps a flaw in our assumptions. The beginning itself offers no refuge. Inflation proposes a violent, sudden expansion at the first instant. It explains much, yet its cause is unknown, its mechanism uncertain. Competing ideas exist, none prevail. And then there is matter itself. It should not be here. Equal parts matter and antimatter should have erased each other. Light without substance, yet matter remained. We remained. The imbalance suggests hidden rules, written into the earliest moments of time. Exploring dark matter and dark energy draws us deeper into uncertainty. These invisible components do not touch light. They cannot be seen directly. Only gravity betrays them. Dark matter reveals itself through motion and distortion. Galaxies rotate too fast. Light bends where nothing visible exists. These effects point to mass without form. Something present, something dominant. Though unseen, dark matter shapes everything. It binds galaxies, guides their motion, sets the framework of the cosmos. Without it, the universe we recognize would not hold together. And that realization offers no comfort. Dark matter remains one of the deepest fractures in our understanding of reality. Many possible particles have been proposed, including WIMPs and axions, yet none have ever revealed themselves. We keep searching, and the silence grows heavier. Across the world, detectors wait underground, shielded from noise. Accelerators strain to recreate what might exist in nature. Still, nothing appears. The mystery does not loosen its grip. Then, there is dark energy, which makes the situation even more unsettling. Dark energy accounts for nearly 70% of everything the universe contains. It is believed to drive the accelerated expansion of space itself, a result that shocked scientists in the late 1990s. Unlike dark matter, it does not gather or clump. It spreads everywhere, evenly, quietly pushing galaxies away from one another. This force runs against gravity rather than with it. One pulls inward, the other drives apart. Understanding this tension may decide how the universe ends, or whether it ends at all. Yet the true nature of dark energy remains unresolved. Debate continues without resolution. It is often linked to the cosmological constant, a term Einstein once placed into his equations, then later regretted deeply. That constant describes an energy built into space itself. Whether this energy stays fixed or shifts over time is still unclear. Some ideas tie it to vacuum energy, others hint at an unknown field or force. None settle the unease. Together, dark matter and dark energy form the hidden framework of the cosmos. They shape structure, they control expansion, yet they remain unseen. This instability in our foundations opens another disturbing possibility. Perhaps our universe is not alone. The idea of other universes forces a quiet crack in certainty. Known as the multiverse theory, it suggests our universe may be only one among countless others. Each could follow different laws, with different constants and different outcomes. This idea did not arise from fiction alone. It emerged from theoretical physics, where equations began pointing beyond a single reality. One route toward this idea comes from cosmic inflation. Inflation proposes that the universe expanded violently just after the Big Bang, smoothing everything we now observe. But some versions of inflation do not stop. They continue elsewhere, at other times, producing isolated regions. These become separate bubble universes, each cut off from the others. In this view, our universe is only one bubble in a vast, unstable foam. The math allows it. The implications are difficult to absorb. String theory deepens this fracture in understanding. String theory replaces point particles with tiny vibrating strings. How those strings vibrate determines particles and forces. Yet the theory allows an enormous number of possible configurations. Each one corresponds to a different version of physical law. This landscape suggests not one universe, but many. The multiverse also offers a way to confront fine-tuning. Certain physical constants appear precisely set for life to exist. Within a vast collection of universes, each with different values, it becomes less shocking that one supports life. We observe it because we can. This reasoning, called the anthropic principle, feels unsettling in its simplicity. It explains by selection rather than cause. Yet even with its appeal, the multiverse remains speculative. Its greatest weakness is clear. It cannot be tested easily. If at all, these universes would be forever beyond reach. No experiment can cross that boundary. The theory drifts between physics and philosophy, offering answers while denying proof. It solves problems by expanding reality itself. And beneath all of this, gravity persists. Weak, yet everywhere. It shapes matter, bends space, and governs motion from the smallest scales to the largest structures. Gravity holds what it can, even as the universe itself seems to slip away. Gravity, framed by Einstein's general relativity as the bending of space-time by mass and energy, quietly governs the universe's uneasy order. It choreographs the motion of celestial bodies and steers the universe's long evolution, even as that order feels fragile. After the Big Bang, everything began as an almost uniform, searing sea of particles. Expansion brought cooling. Cooling allowed small density differences to matter. Gravity seized on those tiny imbalances. Denser regions pulled harder. Gas and dust gathered. The first stars and galaxies emerged, not by design, but by inevitability. Those early structures deepened gravity's grip. They became wells, drawing in more matter, merging, growing. Over time, they formed the vast galactic web we now observe. Nothing about it feels accidental, yet nothing feels secure. Gravity does not stop at creation. It continues to shape how galaxies move, interact, and entangle. Galaxies drift toward one another, assembling into groups and clusters. Filaments connect them, traced by dark matter. This unseen substance makes up roughly 85% of all matter. It bends space-time without ever revealing itself to light, shaping the universe while remaining hidden. Under gravity's pull, galaxies undergo violent transformations. They collide, they merge. These events are not endings, but unsettling rebirths. Gas clouds compress. New stars ignite. Even our Milky Way is not exempt. It is falling toward Andromeda. Their merger, expected in about 4 billion years, stands as a reminder that gravity never releases its hold. On the largest scale, gravity struggles against dark energy. One pulls inward, the other drives space apart. Their tension decides the universe's fate: endless expansion, gradual slowing, or collapse into a big crunch. The answer remains uncertain. That uncertainty echoes everywhere gravity acts, including within stars themselves. Gravity gathers gas and dust to form stars, then dictates their lives. In stellar cores, it creates crushing pressure and heat. Fusion begins. Light is born. When fuel runs out, gravity turns merciless. Stars collapse. Some explode as supernovae, others compress into neutron stars or black holes, objects so dense that even light cannot escape. Gravity also rules quieter realms. It locks planets into orbit. It binds moons to worlds. It sets the paths of comets and asteroids. On Earth, tides rise and fall under the moon's pull, a daily signal that gravity never loosens. Light itself is not free. Gravitational lensing bends it, turning massive objects into cosmic lenses. Galaxies and clusters warp space-time, distorting and magnifying distant light. This effect, predicted by relativity, reveals parts of the universe that would otherwise remain unseen. Images stretch, split, multiply. Reality appears fractured. Yet within that distortion lies clarity. Lensing allows distant, faint galaxies to be studied at all. It exposes their structure, their star formation, their composition. It also betrays dark matter's presence. Though invisible, its mass shapes the lensing pattern. By reading those distortions, astronomers map what cannot be seen. Gravitational lensing takes several forms. Strong lensing creates rings, arcs, multiple images. Weak lensing subtly warps countless background galaxies, its signal only emerging through statistics. Microlensing briefly brightens a star when another passes in front of it, revealing objects otherwise lost in darkness. Through these effects, planets are found. Dark energy is probed, the universe's expansion is questioned, and at the edge of understanding stand black holes, regions where gravity overwhelms everything, where space-time closes in on itself, where escape is no longer a concept. They are not anomalies, they are gravity carried to its final, unsettling conclusion. The formation and evolution of black holes push our grasp of reality to a breaking point. They are born in several ways, yet most often through the death of massive stars. When a star far heavier than the Sun burns through its nuclear fuel, pressure fades. Gravity no longer meets resistance. Collapse begins. The core falls inward under its own weight. If the mass is great enough, the fall does not stop. It tightens into a singularity, a place of infinite density where familiar physics unravels. The rules we trust no longer hold. Around this point forms a boundary, the event horizon. Beyond it, Escape is impossible. Light fails, matter fails. Crossing it marks a one-way passage and the true birth of a black hole. Size follows mass. More mass means a wider horizon, a larger void, a deeper absence. Stellar black holes, born from single stars, are common, yet they do not remain still. They feed. They pull in surrounding matter or collide and merge with others. Over time, this growth can create supermassive black holes, lurking at the centers of galaxies, including our own. Their mass can swell to millions or billions of suns, numbers that feel unreal. Their evolution is studied intensely, yet clarity remains distant. As black holes consume matter, they can unleash narrow jets of particles and radiation. How this happens is still uncertain. Magnetic fields twist. Rotation complicates everything. The picture never fully settles. These emissions reshape their surroundings. Star formation can be altered. Entire galaxies can change course. Black holes also lose mass, slowly, through Hawking radiation. They are not perfectly dark. Quantum effects near the event horizon cause a faint thermal leak. This radiation drains mass over immense spans of time. In theory, a black hole could vanish completely, but the process crawls. Compared to how quickly black holes grow, evaporation is almost negligible, a whisper against cosmic time. Life in the universe rests on balances that feel fragile. Chemical, physical, environmental factors must align. A slight shift, and the structure fails. Central to this balance is the habitable zone, the narrow region where liquid water can exist on a planet's surface. Too close, too far. Either way, life slips away. Water enables the reactions life depends on. Without it, complexity collapses. Yet water alone is not enough. An atmosphere matters. It shields from radiation. It traps heat. It carries gases essential for survival. On Earth, oxygen sustains most life. Carbon dioxide fuels photosynthesis, the base of the food chain. Beneath this lies chemistry. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. These elements assemble into the molecules of life. Carbon stands apart. Its chains are stable. Its versatility is unsettling. Energy is another requirement. On Earth, sunlight dominates. Plants capture it. Life follows. But this view has cracked. Organisms thrive in darkness, near hydrothermal vents, drawing energy from chemical reactions. Light is not the only path. This widens the question. Life may persist without stars overhead if energy exists. Still, stability matters. Temperature swings, atmospheric shifts, radiation spikes. Any of these can erase progress. Complex life needs time without constant disruption. Stable orbits help. Magnetic fields protect. Without them, conditions fracture. The search for life now stretches beyond our solar system. Exoplanets are examined for signs of balance, liquid water, atmospheres, chemistry that might endure. Each discovery sharpens the unease. The universe allows life, but only barely. The discovery of these planets stirs the imagination and unsettles it at the same time. It pushes the search for life beyond Earth further than comfort allows. The question of life elsewhere in the Milky Way has haunted humanity for centuries, drifting between science, philosophy, and fiction, never fully belonging to any of them. As we move deeper into this question, one truth remains hard to face. Despite decades of research and exploration, clear evidence of extraterrestrial life in our galaxy is still missing. The absence lingers, yet the pursuit itself has reshaped what we think is possible and quietly suggests that solitude may not be guaranteed. The Milky Way holds hundreds of billions of stars. Many are likely surrounded by planets. This realization alone weakens the idea of rarity. The discovery of exoplanets, especially those in habitable zones where liquid water might exist, has widened the search far beyond earlier limits. Thousands of exoplanets have now been identified. Among them are worlds that seem capable of supporting life, but habitability is fragile. It depends on more than distance from a star. Atmospheres, magnetic fields, and geological activity quietly decide whether a planet can remain stable or fall apart. An atmosphere can shield life from cosmic radiation and supply gases needed for biology. Geological activity can recycle elements and steady a planet's climate. Astrobiology tries to hold these pieces together. It draws from astronomy, biology, geology, and chemistry to understand how life might arise and survive. It also looks inward, to Earth's most extreme environments, places once thought lifeless. These studies quietly expand the range of what life might endure elsewhere. One of the most promising paths forward lies in reading exoplanet atmospheres. By studying starlight filtered through alien skies, scientists search for gases like oxygen and methane. On Earth, these gases are tightly bound to life. Their presence elsewhere would not be proof, but it would be unsettling. Future telescopes and missions are being built to sharpen this gaze. Each upgrade brings us closer to answers that may not comfort us. The search also turns inward, toward our own solar system. Mars, Europa, and Enceladus hold environments where life could exist, or could have existed, before fading away. Subsurface oceans on Europa and Enceladus, and ancient river valleys on Mars, suggest that life-friendly conditions are not rare accidents. While the search across the Milky Way continues, one fact becomes harder to ignore. The galaxy is crowded with planets and moons that seem capable of hosting life. The lack of evidence does not close the door, it leaves it ajar. As technology advances and understanding deepens, the possibility of life beyond Earth remains unresolved and deeply unsettling. The search itself stretches our knowledge and our tools, forcing us to confront an ancient question that refuses to rest. Are we alone? Or have we never been? This pursuit relies on many methods, reaching from microscopic life to distant civilizations. The study of exoplanets stands at the center. Astronomers detect these worlds indirectly, watching how they disturb their stars. The transit method catches the faint dimming of starlight. The radial velocity method senses the star's subtle wobble. Together, these signals reveal planets that cannot be seen directly. They expose size, orbit, and position within the habitable zone. Technology now pushes further, probing planetary atmospheres for chemical traces of life. By dissecting filtered starlight, scientists search for molecular fingerprints like oxygen, methane, and water vapor. On Earth, these signals mean life. Elsewhere, they would mean the universe is far less stable than we once believed. Future missions promise finer methods, sharper than before, yet still uncertain. They seek traces so faint they may vanish under scrutiny. Another path leads inward, to our own solar system. Robotic explorers on Mars sift through soil and air, chasing hints of microbial life that may have existed or may still linger. Each sample feels like a question without a stable answer. The search reaches farther, toward the frozen moons of Jupiter and Saturn. Europa and Enceladus hide oceans beneath rigid ice, places that seem quiet yet restless. Data from these worlds describe chemistry, fractured surfaces, and signs of internal heat. They point to conditions where life could exist, but never confirm it. Possibility accumulates, certainty does not. The hunt for intelligent life follows a colder logic. SETI listens for signals that nature alone should not make. Radio waves, optical flashes, subtle distortions in starlight that suggest vast engineered structures. Telescopes scan and wait. So far, nothing answers. Still, the silence does not end the search. Instruments grow more sensitive. The listening deepens. Beyond focused missions, scientists also look to fragments and dust. Meteorites that fell to Earth, some traced back to Mars, contain complex organic molecules. Their presence unsettles old assumptions. Between the stars, clouds of gas and dust show similar complexity. The materials of life appear widespread, scattered long before life itself is certain. Then there is the cosmic web, a structure so large it resists intuition. Galaxies and clusters are not isolated. They are bound within vast filaments of dark matter stretched across billions of light years. Dense knots surround enormous voids. The universe looks less like a smooth expanse and more like a fragile lattice. This structure exists because of dark matter, a substance unseen and dominant. It neither shines nor absorbs light, yet its gravity shapes everything visible. Galaxies bend around it. Light curves through space under its influence. We infer its presence without ever touching it, trusting effects over sight. The web began forming soon after the Big Bang. During cosmic inflation, space expanded violently. Tiny quantum fluctuations were pulled open, becoming differences in density. As the universe cooled, gravity took control. Matter flowed inward, abandoning empty regions. Over immense time, filaments emerged. Dark matter formed the frame. Ordinary matter followed. The cosmic microwave background preserves an early image of this process. It shows the universe as it was about 380,000 years after its birth. Slight temperature variations mark denser and emptier regions. These were the seeds. From them grew filaments and voids, the hidden structure beneath everything we see. The filaments are not empty. They carry gas and dust, the ingredients of stars and galaxies. Some stretch hundreds of millions of light years. Where they cross, matter piles up. Galaxy clusters form there, massive and heavy, bending space itself. To study this web is to confront how the universe truly evolves. Astronomers map it through surveys and simulations, assembling a picture that never feels complete. Each result sharpens models of dark matter and dark energy, yet also exposes how much remains unresolved. The cosmos appears ordered, but that order rests on forces we barely understand. The cosmic web stretches across the universe as a vast lattice of dark matter filaments. It is the hidden framework where galaxies are born and shaped. Nothing forms freely. Location, structure, even the rhythm of a galaxy's life are quietly dictated by this web. At its core lies dark matter. Dark matter cannot be seen. It only reveals itself through gravity, yet it outweighs everything else. It forms the rigid backbone of the cosmic web, pulling ordinary matter toward it. Stars, planets, and living things gather not by choice, but by force. In the earliest moments after the Big Bang, matter was spread almost evenly. The balance was fragile. Tiny overdensities appeared, barely noticeable. Dark matter amplified them. Gravity took hold. Matter drifted inward. These small irregularities became the seeds of the cosmic web, and later, of galaxies themselves. As gravity tightened its grip, gas and dust flowed into the densest regions. Where dark matter filaments crossed, deep gravitational wells formed. The first galaxies emerged there. The filaments acted as channels, guiding matter toward these nodes. Clusters and superclusters grew where the pull was strongest. This was never a finished process. It continues. Galaxies still draw material from their surroundings. New stars ignite. Shapes change. Growth never truly stops. The web also controls how galaxies meet. Those bound to the same filament drift toward shared centers, collide, and merge. These encounters are not rare accidents. They are inevitable. Mergers can spark intense bursts of star formation. Spiral galaxies can collapse into elliptical forms. Over time, position within the web leaves its mark. Galaxies in dense regions grow old faster. They turn red. Their gas runs out. Star formation fades. In thinner filaments, galaxies remain younger and bluer, still forming stars, still unsettled. Feedback complicates this fragile balance. Exploding stars and active galactic nuclei release energy into their surroundings. Gas heats up, collapse slows or stops. Star formation is restrained. Even the web itself feels these effects over cosmic time. The cosmic web is not an abstract idea. It is supported by observation and theory converging on the same unsettling picture. The universe's large-scale structure matches what models predict. Galaxy surveys have mapped this pattern in detail. Millions of galaxies reveal a filamentary arrangement, not a random scatter. They trace long strands around immense voids where almost nothing exists. What we see follows what dark matter silently enforces. Gravitational lensing deepens the unease. Massive structures bend light from distant galaxies, distorting what we observe. These distortions map unseen mass. The patterns align with dark matter filaments, exactly where the cosmic web says they should be. Simulations echo the same story. From early conditions after the Big Bang, virtual universes evolve into webs of filaments and voids. The resemblance to reality is hard to dismiss. Even the space between galaxies betrays the structure. The intergalactic medium absorbs light from distant quasars. Thin absorption lines appear. They trace hydrogen gas stretched along invisible filaments. The web leaves marks even where matter seems absent. The universe, it seems, is not open or neutral. It is structured, constrained, and held together by something we cannot see, shaping everything while remaining just out of reach. The expansion of the universe is not galaxies fleeing through space from some hidden center. It is space itself giving way, stretching, carrying everything with it. Galaxies do not run, they are carried. The familiar image of dots on an inflating balloon helps, but it also unsettles. There is no center on the surface, no privileged place, only distance growing everywhere at once. This view explains how galaxies drift apart without pointing to an origin we could stand inside. Evidence comes from the cosmic microwave background, a faint afterglow from the universe's earliest moment. Its smoothness across the sky suggests a past that was hot, dense, and tightly packed, now thinned and cooled by relentless expansion. The speed of this expansion is captured by the Hubble constant, a measure linking distance to recession. Yet when we try to pin it down, the numbers refuse to agree. Measurements from the early universe clash with those from the nearby one. The mismatch is small, but disturbing. It hints that something in our picture is missing. As if that were not enough, the expansion is not slowing, it is speeding up. This was uncovered through distant supernovae, their light dimmer than expected, their distances larger than they should be. The cause is called dark energy, a name that explains little. It fills all space, it pushes outward, it works against gravity. We believe it makes up most of the universe's energy, yet we do not know what it is. The ground feels less solid when you realize that what dominates reality is something we cannot describe. The future bends with this uncertainty. If dark energy holds steady, expansion will never end. Space will thin, heat will fade, galaxies will slip beyond reach in a slow, silent freezing. If dark energy changes, other endings appear. Collapse, rupture, a tearing so extreme that even atoms fail. Each outcome grows from the same simple fact: space is not stable. This expansion shapes galaxies themselves. It does not just separate them, it guides how they form, how they grow, how they meet their end. On the largest scales, galaxies recede from one another in every direction. No matter where you stand, the view is the same. Distance grows faster the farther you look. It feels fair. It is also unsettling. Yet expansion is not absolute. Gravity still resists. In small regions, galaxies remain bound. Our Milky Way does not drift freely. It is locked with Andromeda, drawn together despite the universe pulling everything apart. They will collide. They will merge. Expansion allows this contradiction. Things separate on vast scales, yet still crash together nearby. As space stretches, it reshapes the distribution of matter. Dark matter lays down an invisible scaffold, vast filaments and dense knots. Ordinary matter follows, collecting where gravity allows. Galaxies emerge along these structures, shaped by forces we cannot see directly. Even light is altered. As it crosses expanding space, its waves are stretched, colors shift toward red. Time itself seems encoded in this change. Redshift lets us measure distance, age, and history. It lets us look backward, toward galaxies as they were when the universe was young. The more we observe, the clearer one thing becomes. The universe is not fixed, it is opening beneath us. And the more precisely we measure it, the more fragile our certainty feels. The future of galaxies is tied to how the universe keeps expanding and to what dark energy truly is. If the expansion keeps accelerating, as observations imply, distant galaxies will slowly slip away. Their light will be stretched until it can no longer be seen. The sky will empty. The universe will feel sparse and isolating. with each galaxy trapped inside its local group, surrounded by an ever-expanding void. Magnetic fields are invisible, yet they quietly shape the cosmos. They influence countless processes across the universe. They are not isolated effects. They are woven into everything, from planets and stars to the immense spaces between galaxies. They are everywhere, yet rarely felt directly. Inside stars, including the Sun, magnetic fields arise through dynamo action. Moving, electrically conducting plasma generates magnetic energy. From this come sunspots, violent flares, and massive eruptions that tear through stellar atmospheres. These events are not distant curiosities. They can disturb satellites, disrupt power systems, and paint Earth's skies with auroras. On larger scales, magnetic fields guide the life cycle of stars. In cold, dense clouds of gas and dust, where stars are born, these fields influence how collapse unfolds. They affect how fast stars form and how massive they become. They steer gas and dust inside, rotating disks around young stars, shaping the early stages of planet formation. Magnetic fields are also embedded in the interstellar medium, the thin mixture of gas and dust between stars. They help support clouds against gravity. They regulate star formation. They guide charged particles as they move through galaxies. Through this constant interaction, magnetic fields quietly influence how galaxies evolve and how matter is arranged within them. Beyond individual galaxies, magnetic fields persist. They exist inside galaxy clusters, the largest structures held together by gravity. There, turbulent motion can amplify them until they stretch across millions of light years. These vast fields affect the paths of cosmic rays, particles racing through space at nearly the speed of light. Where these magnetic fields come from remains deeply uncertain. Some may have formed in the early universe, then grown stronger over cosmic time through complex processes. If this is true, they carry traces of the universe's earliest conditions. Understanding them could reveal how cosmic evolution truly began. Yet these fields resist direct observation. They do not shine. They do not announce themselves. Astronomers must infer their presence through subtle clues, through polarized light or the motion of charged particles. Slowly, with better tools and models, pieces fall into place. What emerges is a universe shaped by forces we cannot see, held together by structures that feel unsettlingly fragile. In both star and galaxy formation, magnetic fields act as an unseen framework. They are not passive. They actively shape how gas and dust behave. From the very beginning of star birth, their influence is present. Stars form inside molecular clouds, vast reservoirs of gas and dust. Within them, magnetic fields interact with charged particles, altering how gravity pulls the cloud inward. In some directions, collapse is slowed. The cloud stretches and distorts. The pace of star birth changes. As collapse continues, magnetic field lines tighten and concentrate. They guide material onto the growing star and help control its growth. They also shape the formation of rotating disks around newborn stars. These disks become the environments where planets may one day emerge, fragile structures balanced by forces that remain mostly unseen. Magnetic fields quietly pull angular momentum away from the heart of a disk. Because of that loss, matter can slip inward toward a forming star. At the same time, the disk itself feels less certain. Its stability wavers. The path toward planet formation is subtly altered. On far larger scales, during the shaping of galaxies, these fields are still at work. Their exact role in the birth of galaxies is not fully settled. That uncertainty remains. Yet once galaxies exist, the influence of magnetic fields is undeniable. They seep through the interstellar medium, steering charged particles and shaping the faint structure between stars and beyond them. They quietly decide how gas enters and leaves galaxies. That flow controls how fast stars appear and how galaxies grow across time. Inside galaxy clusters, magnetic fields stretch through the space between galaxies. They act on the hot, ionized gas filling that darkness. Cosmic rays change course. The intracluster medium shifts. shock waves, and turbulence carry their mark. Through all of this, the thermal history of clusters is rewritten, and the lives of their galaxies are slowly redirected. Studying these fields is difficult. They do not reveal themselves easily. Progress depends on fragile signals and demanding models. Polarized light bends in their presence. Synchrotron radiation traces electrons spiraling along invisible lines. Simulations now try to include these forces, knowing that without them, the universe we model feels incomplete. The interstellar medium sits between stars, but it is not empty. It never was. It is a restless mixture of gas, dust, and cosmic rays, essential to how galaxies breathe and change. Nearly all of it is gas, with only a small fraction of dust by mass. Hydrogen dominates, atomic and molecular. Helium follows. Heavier elements exist only in traces, yet their presence matters. Dust appears insignificant, but it carries silicates, carbon compounds, and complex organic molecules. Some hint at chemistry that feels uncomfortably close to life. Conditions within the ISM vary wildly. In dense molecular clouds, temperatures fall below 100 Kelvin. These dark, cold regions allow stars and planetary systems to begin. Elsewhere, near massive stars and supernova remnants, temperatures climb past 1,000,000 Kelvin. This contrast fractures the ISM into distinct regions. Molecular clouds stand cold and dense, where molecules survive and stars emerge. H2 regions glow under harsh ultraviolet light, hydrogen stripped of electrons by young stars. Warm, neutral, and warm ionized mediums fill much of the volume, unstable bridges between phases. Hot ionized regions, born from supernovae, stretch across hundreds of light years, carrying immense energy and reshaping their surroundings. Magnetic fields thread through all of this. Cosmic rays pass through at near light speed. Together, they interfere with gas and dust, bending flows and altering collapse. Clouds do not fall inward freely. Ionization increases. Chemistry shifts. Nothing proceeds untouched. Matter in the ISM is never at rest. Stars condense from its densest pockets. Later, through winds, nebulae, and explosions, they return material back to it. Each cycle enriches the medium with heavier elements. Those elements wait, quietly, to become part of new stars and new worlds. The process repeats, but never in quite the same way. The interstellar medium is not a silent backdrop. It is deeply involved, quietly shaping how stars come into being. It holds the material, sets the conditions, and waits. Gravity, gas, and dust move together inside it, forming a fragile balance that underpins one of the universe's most basic acts. Star formation begins where the ISM grows dense, inside molecular clouds. These stellar nurseries are cold and lightless. Temperatures sink below 100 Kelvin. Within them lie molecular hydrogen, helium, dust, traces of heavier elements, and complex organic compounds. Everything needed is there, yet nothing feels stable. The cold and the shielding dust keep energies low enough for molecules to survive. Then something shifts. Portions of a cloud begin to collapse under their own gravity. The trigger can come from outside, a nearby supernova shock, the pull of a passing star, the pressure from ionized regions around massive stars, small disturbances, large consequences. Once collapse starts, it deepens. A dense core forms. The cloud breaks apart into fragments, each carrying the possibility of stars. As contraction continues, rotation speeds up. Matter flattens into disks. Protostellar disks emerge, circling stars that are not yet fully born. These disks do more than shape stars. They quietly set the stage for planets. Entire solar systems may take form there. Meanwhile, invisible forces interfere. Magnetic fields slow or redirect collapse, altering how fast stars form and how massive they become. Cosmic rays slip through the densest regions. They ionize gas. They enable chemical reactions that should not exist in such cold darkness. The chemistry of star-forming regions grows more complex, less predictable. Even so, star formation is inefficient. Most of the gas never becomes stars. It is pushed back into the ISM by stellar winds, radiation pressure, and supernova explosions. What remains is enriched. Heavier elements return to the medium, seeding future generations. The cycle continues, without pause. The ISM never finishes its role. It constantly reshapes galaxies through this slow exchange. Molecular clouds provide raw material. Physical and chemical processes decide outcomes. Stars and planetary systems emerge, carrying the imprint of these unstable beginnings. Nebulae are vast clouds of dust, hydrogen, helium, and ionized gas. They glow across space, often labeled as stellar nurseries. Under dark skies, some are visible, even to the naked eye. Their beauty feels deceptive. Beneath it lies motion, pressure, and collapse. The word nebula means cloud. The name fits. These diffuse structures vary in shape and scale, each playing a different role in stellar life cycles. They move matter and energy through the galaxy, quietly sustaining it. Emission and reflection nebulae mark regions where gravity gathers raw material into new stars. Gas flows, magnetic fields, and radiation collide within them. Dark nebulae, heavier and more opaque, hide future stars within their dust. Inside, matter collapses, protostars form, ignition waits. As this journey through the galaxy ends, certainty fades. Questions remain. Did everything truly emerge from nothing, or is something missing from our understanding? And even if we find it, will we be capable of grasping what it means? What do you think? Leave your thoughts below, subscribe for more, and thank you for watching.